Night after night, long before civilization built cities or wrote words on parchment, human beings looked up in wonder at the sky. In the darkness above untouched plains and forests, an endless tapestry of stars shone down, with no scientific instruments and no recorded formulas. Those first skywatchers relied on their eyes, their stories, and a deep curiosity. They gathered around crackling campfires and pointed out patterns in the sparkling night. Under a sky unspoiled by any man-made light, the universe must have felt immense, yet intimately close. A dome of mystery arching over the little world of human concerns. In those prehistoric times, the sky served many purposes at once. It was a calendar, a clock, a guide, and a source of wonder. The slow dance of the sun, moon, and stars across the heavens told our ancestors when the seasons were turning, when the cold of winter would give way to spring's renewal. By watching the sunrises and sunsets, they learned to anticipate the longest day of summer and the longest night of winter. Each new moon and full moon marked the passage of time in a world without mechanical clocks. For people whose lives depended on the migrations of animals and the ripening of wild plants, these celestial patterns were essential knowledge, the difference between hunger and plenty. Beyond survival, the sky was a canvas for the human imagination. Every culture began to weave stories into the stars. They saw figures in the constellations, a great hunter chasing his prey across the night, a proud queen sitting among the heavens, a wandering hero immortalized in the stars. Tiny clusters of lights became legendary animals or ancestors watching from above. These myths gave meaning to the glittering points of light. To early humans, the sky was alive with deities and spirits. A bright star appearing at dusk might be a benevolent guardian. A comet streaking unexpectedly through the sky could be an omen from the gods. Each sunrise was a triumph of light over darkness, and each eclipse a moment of cosmic uncertainty that could send people to their knees in awe or fear. Imagine a clear, moonless night, tens of thousands of years ago. A small band of people gathers under a sky brimming with stars. Perhaps an elder lifts a hand and points to a familiar cluster, maybe what we call Orion's belt, 3 bright stars in a row, and begins to recount a story tied to that pattern. The others, young and old, listen closely, faces lit by firelight as much as by starlight. In that moment, storytelling and astronomy are one and the same. The stars become theatre for myth, and the act of observing them becomes a ritual passed from one generation to the next. Around that fire, under that vast sky, knowledge is not written in books, but etched in memories and shared in spoken tales. Over time, these observations grew more keen. People noticed that certain stars rose in the east at dawn only during particular seasons. For instance, much later in history, the Egyptians would note the star Sirius rising at sunrise, just before the Nile River flooded each year, a crucial piece of information for agriculture. Long before that, early hunter-gatherers surely learned that the appearance of specific stars, or the phase of the moon, could signal when herds migrated or fruits ripened. By paying close attention to the heavens, our distant ancestors found a reliable guide to life's rhythms on Earth. Here and there, evidence survives of this prehistoric astronomy. Deep in caves in France and Spain, alongside ancient paintings of bison and horses, there are dots and symbols that some researchers interpret as star maps or lunar calendars. A series of dots painted in the Lascaux cave, dating back 17,000 years, might represent the phases of the moon, or even a constellation like the Pleiades cluster. In Germany, Archaeologists discovered a carved mammoth tusk over 30,000 years old, with patterns of notches that could correspond to the cycle of the moon or the stars in Orion. We cannot be certain that these are intentional sky records, but they tantalize us with the possibility that even in the last ice age, humans were charting the heavens in their art and artifacts. As generations passed, knowledge of the sky deepened and was passed down through oral tradition. Early humans moved from purely hunting and gathering towards settled life, and with that change, the sky's importance only grew. The moon's roughly 29-day cycle provided an easy way to count out the length of a month. Many early communities linked the moon's cycle to female fertility or to the planting of crops, reinforcing the idea that human life was connected to celestial rhythms. Rituals and ceremonies often aligned with celestial events. A tribe might hold a celebration on the night of the full moon, or a day of reflection at the winter solstice, when the sun reached its lowest arc in the sky and the year's longest night arrived. For these ancient people, observing the sky was not just practical, it was often sacred. The earliest priests or shamans were likely skilled sky watchers. They studied the heavens for signs from the divine. A sudden new star, what we now know as a nova, flaring into view, or a lunar eclipse darkening a full moon, could send a ripple of alarm or wonder through a community. During a solar eclipse, when daylight mysteriously faded and the sun seemed to be swallowed by darkness, we can imagine the eerie silence that might fall over a gathering of people. Birds would hush, the air would cool, and a sense of dread or awe would grip everyone until the sun's light returned. To appease or understand such cosmic events, early societies developed rituals, perhaps banging drums or offering prayers when the sun was in eclipse, in hopes of bringing back the light. Through myth and ritual, early skywatchers laid the groundwork for astronomy without yet knowing the science behind it. By carefully observing the changing heavens, they learned to predict seasonal changes and celestial events in a rudimentary way. They might not have understood why the sun rose a little farther south or north each day throughout the year, but they knew it happened and marked those extremes. Many of their rituals, dances, feasts, or commemorations coincided with these celestial milestones, inscribing the sky's pattern onto their cultural calendars. In doing so, they preserved vital knowledge, the time to start a long migration, the best moment to begin harvesting and storing food, or the omen of an approaching winter. Under the same sky that arches over us tonight, those ancient observers noticed something peculiar too. A few star-like points of light that moved against the background of the fixed stars. These were the wanderers, the planets. To the unaided eye, Mercury, Venus, Mars, Jupiter, and Saturn looked like bright stars. But unlike the true stars, they changed position noticeably over weeks and months. Early skywatchers tracked these wanderers as well, weaving them into their myths as gods or spirits roaming the heavens. The wandering of Mars or Venus in the sky may have been associated with particular deities of war or love. Though they could not yet decipher the planet's complex paths, people's recognition that not all lights in the sky are the same was another step toward a more systematic curiosity about the cosmos. Thus, in the long ages before formal science, humanity's romance with the stars began. The night sky was a grand mystery, but through patience and imagination, patterns emerged and became familiar friends. People found comfort and meaning in those patterns. A certain star rising before dawn might herald cooling weather or the time of a ceremonial gathering. A cluster of stars overhead in autumn might remind them of loved ones lost, now believed to dwell in the heavens. By observing and remembering, the first astronomers, though they would not have called themselves that, slowly built a base of knowledge. It was fragile and interwoven with legend, yet it was real knowledge, born of careful attention. Millennia passed. Those first Skywatchers' descendants carried on their careful observations, and as human societies grew more complex, as we formed villages, then towns, then the first great civilizations, our ability to record and organize knowledge grew too. What began as a campfire story or a carved symbol became lists of celestial sightings, primitive calendars, and eventually deliberate alignments of structures with the sky. The earliest chapters of astronomy were written in the languages of myth and ritual, but the stage was set for a new chapter. As the Neolithic age gave way to the age of cities and agriculture, people were ready to transform star lore into structured knowledge. The first civilizations would soon begin mapping the heavens in earnest, marking the true beginning of astronomy as an organized endeavor. As human societies moved from nomadic life to settled villages and then to the first cities, their fascination with the sky did not diminish. It deepened. The scattered observations of earlier millennia began to accumulate, forming a body of knowledge that could be shared, preserved, and refined. Across the world, ancient peoples started to map the heavens with intent and ingenuity. They found regularity in the movements above and used those patterns to shape calendars, guide agriculture, and inspire their cosmologies. The heavens held clues to the timing of rains and harvests, of migrations and festivals. By recording the positions of the sun, moon, and stars, civilization found a kind of cosmic rhythm, a reassurance that the sky's patterns were reliable, even as human fortunes rose and fell. One striking example of early sky mapping still stands on England's Salisbury Plain, the great circle of stones at Stonehenge. Some 4,500 years ago, people raised this ring of giant stones and carefully aligned it with the movements of the sun. Each year, on the summer solstice, the longest day, the rising sun climbs exactly above the heelstone and casts its light through the heart of the circle. Even today, crowds gather at dawn on that day to witness the sun's first rays framed by Stonehenge's ancient pillars. To its builders, this was surely a moment of both practical and spiritual significance, a celebration of the year's turning point, when days would slowly begin to shorten. Stonehenge was more than a collection of rocks. It was part observatory, part temple. Its stones and openings marked the passage of time in a monumental way. We can imagine Neolithic people gathered among those stones in pre-dawn darkness, awaiting the sunrise on the longest day. When the sun finally broke the horizon and that beam of sunlight pierced the monument, it would have confirmed that the cycle of seasons was continuing as expected. It was both a practical marker and a deeply symbolic event, offering a sense of order and connection between their world and the sky. Stonehenge was not alone. Throughout the ancient world, many cultures built structures aligned with celestial events. In Ireland, the Neolithic tomb of Newgrange, built around 3200 BC, was engineered so that at dawn on the winter solstice, a shaft of sunlight would travel down a long passage and illuminate its inner chamber, a triumphant symbol of light returning on the year's darkest day. In ancient Egypt, the pyramids at Giza were oriented almost perfectly north-south, and temples were constructed to align with the rising sun or certain stars, tying their earthly architecture to cosmic order. Farther afield, in what is now the Sahara Desert, an even older site at Nabta Playa, circa 5000 BC, featured stones arranged to mark where the sun rose at the summer solstice. These examples show that long before the written word, people around the globe took great care to observe the heavens and build what we might call the first observatories. By aligning stones or temples with the sun's path or the rhythm of the stars, they created permanent calendars in the landscape and sanctified their connection to the cosmos. While monoliths and temples captured the sun's seasonal dance, ancient scribes began to record the night sky's more intricate patterns. In Mesopotamia, the cradle of civilization between the Tigris and Euphrates rivers, astronomy became a scholarly pursuit as early as 1000 BCE, and even before. There, priests and court scholars watched the skies from the tops of ziggurats, the stepped temple towers of cities like Babylon. Night after night, they noted the rising and setting of stars and planets, and wrote these observations on clay tablets in cuneiform script. Some of the oldest star catalogues come from this region. The Babylonians, inheritors of Sumerian star lore, identified constellations and tracked planetary movements systematically. They divided the sky into regions, a tradition that eventually yielded the concept of the zodiac. 12 constellations along the sun's yearly path. By around 1200 BCE, a compendium of Babylonian astronomy known today as the MUL-APN tablets listed dozens of stars and their motions through the seasons, essentially serving as an early handbook for sky watchers. From such records came remarkable predictive power. Babylonian astronomers, through centuries of observations, learned to anticipate certain celestial events. They could predict lunar eclipses by recognizing the repeating cycle in which they occur. They tracked the wandering planets, Mercury, Venus, Mars, Jupiter, and Saturn, noting how these wandering stars sometimes slowed, stopped, or even moved backward, retrograde, against the starry background. Using clever arithmetic schemes, Babylonian scholars developed methods to forecast these motions. For instance, they knew when bright Venus would reappear in the dawn sky after months of being invisible, or when Jupiter would return to a particular constellation. To the people of that time, these predictions were not just scientific curiosities, they were entwined with astrology and statecraft. Celestial events were seen as omens, so being able to predict them gave political and religious leaders a sense of control or forewarning about the future. Indeed, in Mesopotamia, astronomy and astrology were two sides of the same coin. The night sky was regarded as a kind of divine script, the gods communicating through celestial signs. Every eclipse of the sun or moon, every appearance of a comet or a rare alignment of planets was thought to foreshadow events on Earth. Mesopotamian scholars compiled extensive omen lists. For example, a tablet might record that, if an eclipse occurs in this month, a great king will die, tying sky events to earthly outcomes. While we remember those interpretations as superstition, the effect on astronomy was to motivate extremely careful observation and record-keeping. In trying to read the will of the gods in the sky, these ancient observers inadvertently laid down a foundation of rigorous data. Their clay tablets, baked hard and preserved, contained detailed reports of planetary positions and star appearances over centuries. In hindsight, they were doing science, even if their intent was to serve theology and royal interests. Ancient astronomy blossomed in other parts of the world as well. In China, court astronomers, by at least 700 BCE, and likely much earlier, were recording eclipses and the passage of comets, considering these events to be omens that could legitimize or threaten an emperor's reign. The Chinese developed their own star maps and identified dozens of constellations different from those of Mesopotamia or Greece. They tracked planetary motions and even noted unexpected guest stars, novae or supernovae, that flared up in the sky. In the Americas, the Maya civilization, at its height between about 250 and 900 CE, crafted elaborate calendars rooted in celestial cycles. They observed the motions of Venus with particular care, timing certain wars and rituals to the planet's appearances as morning or evening star. They built observatories, such as the Caracol in Chichen Itza, with windows aligned to the equinox sun and the extremes of Venus's rise and set. Though separated by great distances and cultures, these civilizations all found order and guidance in the sky. Careful skywatching became a universal language of timekeeping and prophecy. By the time of classical Greece, around 500 BCE and onward, the accumulated astronomical knowledge of older civilizations was being absorbed and reinterpreted through the lens of Greek philosophy and geometry. Greek scholars traveled to Babylon and Egypt, learning about calendars, star catalogues, and mathematical techniques developed there. They brought home ideas like the 19-year Metonic cycle for harmonizing lunar and solar calendars, and they adopted the Babylonian division of circles into 360 degrees. The Greeks began to seek not just patterns, but principles. As early as the 6th century BCE, Pythagoras and his followers suggested that nature was built on numbers, and that the motions of the heavens might follow mathematical harmony. By the 4th century BCE, Aristotle taught that Earth was a sphere, noting the curved shadow it cast on the moon during eclipses, and placed Earth at the center of a finite cosmos of concentric crystalline shells. Around 240 BCE, in Egypt, Eratosthenes calculated Earth's circumference with astonishing accuracy. This showed how quantifiable the cosmos could be when one combined observation with geometry. While most Greek thinkers accepted a geocentric cosmos, there were noteworthy exceptions. In the 3rd century BCE, Aristarchus of Samos proposed that the Earth and other planets actually orbited the Sun. His heliocentric theory was far ahead of its time and gained little traction then, but it shows that the concept of a sun-centered system existed well before Copernicus. Meanwhile, Greek astronomers continued to refine the observational side of astronomy. In the 2nd century BCE, Hipparchus of Nicaea compiled a star catalogue of roughly 1,000 stars, noting their positions and brightnesses. He noticed that the positions of stars were not entirely fixed over long periods. By comparing his catalogue to observations from a century or more earlier, he discovered the gradual wobble of Earth's axis, known as the precession of the equinoxes. The level of precision the Greeks achieved with simple instruments, like sighting tubes and graduated circles, was remarkable. By the dawn of the 1st millennium AD, the sky had been charted and measured as never before, and intricate geometrical models, with circles and epicycles, were being used to predict the motions of the planets. All these developments set the stage for a towering synthesis. In the 2nd century AD, in Alexandria, Egypt, a great center of learning of the ancient world, an astronomer named Claudius Ptolemy would take up this rich legacy of observations and theories. He would create an encompassing model of the cosmos that would endure for over a millennium. The era of the first sky watchers, of stone circles and star lore, had evolved into an era of calculated predictions and celestial charts. The transition from mythology to science was gradual, but by Ptolemy's time, it was in full bloom. The story of astronomy was about to enter a new chapter, as the old Earth-centered ideas reached their most refined form, awaiting the challenge of a sun-centered revolution to come. In the 2nd century AD, in the city of Alexandria, an astronomer named Claudius Ptolemy set out to synthesize all existing astronomical knowledge into a single system. Drawing on observations from Greece, Babylonia, and his own era, Ptolemy crafted a grand model of the cosmos, with Earth immovably at its center. This geocentric model would dominate human thought for over a millennium. It was both mathematically elaborate and philosophically satisfying to the people of that time. Earth, in Ptolemy's universe, was the hub of all celestial motion, a natural assumption, since it feels as if the ground beneath us is still and everything in the sky turns around us. In Ptolemy's model, the Earth was orbited by a series of concentric spheres. Nearest was the Moon's sphere, circling Earth roughly once a month. Next came Mercury, then Venus, each on its own transparent shell. Beyond them, the Sun itself revolved around Earth in a daily journey that brought day and night. Farther out were the spheres of Mars, then Jupiter, then Saturn, the outermost planets known in antiquity, each taking longer to complete its circuit. Finally, at the greatest distance, lay the sphere of the fixed stars, an immense shell on which all the constellations were embedded, rotating daily to produce the rising and setting of stars. Some philosophers even imagined an outermost layer, the prime mover, that gave the entire cosmic system its motion. To people of Ptolemy's time, this structured, Earth-centered cosmos was comforting and ordered. The heavens were finite, noble, and revolving with Earth and humanity at the focal point. But the planets, the wandering stars, posed a challenge. Observers for centuries had noted how planets like Mars and Jupiter did not move at a steady pace along their paths. At times, a planet would slow down, halt, and even drift backwards, retrograde, for a while before resuming its forward motion against the background stars. How could this be? Ptolemy's ingenious solution was to introduce a system of circles upon circles. He supposed that each planet moved in a small circle of its own, an epicycle, even as it travelled on a larger circle, called a deferent, around Earth. By tuning the sizes and speeds of these epicycles, Ptolemy could account for the looping, backtracking paths of the planets. This mathematical contrivance made the geocentric model quite accurate in its predictions. Using Ptolemy's tables and algorithms, one could predict where, say, Mars would appear in the sky on a given date, or when Venus would be visible at dawn or dusk. For the needs of calendar makers, navigators, and astrologers, the system was sufficiently precise. Ptolemy presented his comprehensive model in a work that later generations called the Almagest, meaning the greatest. The Almagest was a treatise encompassing all aspects of astronomy as known to the Greco-Roman world. In it, Ptolemy detailed the geocentric model's mechanics and provided step-by-step instructions for calculating celestial positions. He included a star catalogue with over 1,000 fixed stars, listing their coordinates and brightness, a legacy of earlier astronomers. The Almagest became the astronomical Bible for scholars from its publication in the 2nd century AD through the medieval era. Long after the Roman Empire fell, astronomers in the Islamic world translated and studied Ptolemy's work. They called it Al-Magisti and expanded upon it. It crossed into medieval Europe via those Arabic translations and formed the foundation of astronomy taught in universities. For century upon century, to question Ptolemy's model was to question the accepted understanding of the cosmos itself. Part of the model's enduring power was how well it harmonized with philosophical and religious ideas. In Ptolemy's time, and for long after, it was believed that the celestial realm was fundamentally different from Earth. Earth was the realm of change and decay, but the heavens beyond the moon were perfect and unchanging. Circular motion was seen as the most perfect, divine form of movement. Ptolemy's system, with planets on crystalline spheres moving in circles, aided by epicycles, fit that ideal. It also placed Earth at the center. Later, medieval Christian thinkers would adopt this cosmology wholeheartedly, embedding the Earth-centered cosmos into a theological framework. Earth, with mankind, was at the center of creation, and the celestial spheres were the abode of angels and God. The Ptolemaic cosmos was thus not only a physical model, but a deeply moral and spiritual one. It gave people the sense that they knew their place in the universe, at the center, fixed and significant, with the cosmos literally revolving around them. Ptolemy's model proved resilient. Through the centuries, as observations became more precise, scholars tweaked the system, adding a small epicycle here or adjusting a sphere's speed there to better match new data rather than abandon the Earth-centered scheme. In the medieval Islamic world, astronomers like Al-Tusi and al-Battani refined Ptolemaic calculations and even pointed out inconsistencies like subtle changes in the moon's motion. Yet the core framework remained unchallenged. In Europe, the Ptolemaic model, merged with Aristotelian physics, became dogma. It was taught alongside scripture as the obvious order of God's creation. By the 15th century, however, the compounding of minor discrepancies and the sheer complexity of the epicycle-laden model made some thinkers uneasy. The cosmic machine, built of dozens of interlocking circles, had grown cumbersome. There was a growing sense that nature's true design might be simpler than this artifice. The stage was set for a radical rethinking of the cosmos, one that would shift the center of the universe from Earth to the Sun. In the early 1500s, a Polish cleric and scholar named Nicholas Copernicus quietly developed a radical theory that the Sun, not Earth, was at the center of the known universe. After years of study and calculation, he concluded that placing the Sun in the middle made the motions of the planets far more orderly. In his heliocentric model, Earth became one of the planets, orbiting the Sun just as Venus or Mars did. The Moon alone continued to circle Earth, but all the other planets revolved around the Sun. Copernicus also proposed that Earth spins on its axis once a day, causing the daily rising and setting of the Sun, stars, and planets. This simple shift, a moving Earth and a stationary Sun, was a revolutionary change in perspective, one that Copernicus knew would be controversial. Copernicus was cautious about broadcasting his idea. For decades, he circulated his heliocentric theory only among friends and fellow scholars. He waited until 1543, the year of his death, to publish his great work on the revolutions of the heavenly spheres. According to later tales, Copernicus received the first printed copy on his deathbed. Whether fact or legend, the heliocentric theory had finally entered the public arena. Initially, however, it did not cause an uproar. To most learned contemporaries, Copernicus's proposal was seen as a useful mathematical hypothesis, not necessarily as a literal description of the cosmos. After all, if Earth was hurtling through space, why didn't people feel it move? Why didn't objects fly off the spinning globe? And if Earth orbited the Sun, why did the constellations not change their positions over the year, the expected parallax effect? Copernicus and his supporters argued that the stars were so distant that any parallax was too small to detect with the naked eye, implying a universe vastly larger than previously imagined. Even so, many scholars remained skeptical. And since Copernicus still assumed the planets moved in perfect circles, his model, while conceptually simpler, did not dramatically improve the accuracy of planetary predictions at first. It was a bold idea that lacked solid observational proof in its early years. Over time, the Copernican model began to attract a few bold advocates who saw an elegant truth in it. They viewed the sun-centered system as a beautiful simplification of the cosmic mechanism, a graceful clockwork that no longer required awkward adjustments. To these early heliocentrists, It was as if the cosmic stage had been rearranged to put the brightest actor, the sun, at the centre, and everything made more sense as a result. But the idea remained largely theoretical until further evidence could be found. By the early 1600s, that evidence was on the way. The stage was set for new discoveries, both observational and theoretical, that would firmly vindicate Copernicus's vision. A new generation of astronomers was coming, armed with the telescope and guided by mathematics, ready to transform the Copernican hypothesis into demonstrable reality. In 1609, the same year that Johannes Kepler published his first 2 laws of planetary motion, an Italian mathematician named Galileo Galilei pointed a new invention toward the night sky. The invention was the telescope, a simple tube with lenses, and for the first time in history, human eyes saw the heavens magnified. Galileo's observations would open a new chapter of astronomy. When he looked at the moon, he saw mountains and craters, realizing that the moon was not a perfect, ethereal orb, but a world with terrain much like Earth. He turned his telescope to the planet Jupiter, and was astonished to find 4 small stars orbiting it. In reality, 4 moons circling a planet, a miniature planetary system. This clearly showed that not everything in the cosmos revolved around Earth. Night after night, Galileo sketched the positions of these Jovian moons as they moved around Jupiter, providing undeniable evidence of orbital motion around a center other than Earth. Everywhere Galileo looked, he challenged old assumptions. He observed that Venus went through a full cycle of phases, from a thin crescent to a full disk and back, just like the moon. The Ptolemaic geocentric model could not easily explain that phenomenon, but the Copernican heliocentric model could. In a sun-centered system, Venus circles the sun on an orbit inside Earth's, and we see different portions of its sunlit half as it moves around. Exactly what Galileo observed. He also noticed spots on the sun, blemishes that appeared and vanished and drifted across the solar disk. This was evidence that the sun itself rotated, and that it was not the flawless, unchanging body philosophers had imagined. Even the planet Saturn perplexed him. His telescope showed odd lobes or ears on either side of Saturn. We now know he was glimpsing Saturn's rings, though his instrument was too crude to discern them clearly. And when Galileo trained his telescope on the Milky Way, what looked to the naked eye like a milky cloud resolved into countless faint stars. The universe, it appeared, held far more stars than could be seen without aid, and they were scattered across immense distances. Galileo eagerly published his discoveries in 1610 in a booklet titled The Starry Messenger. The news spread quickly across Europe. Some greeted it with wonder and excitement. The cosmos was not what they had assumed. Others, especially certain authorities in the Catholic Church, met Galileo's findings with skepticism and hostility. The idea that Jupiter had moons, or that the sun had spots, wasn't inherently heretical, but Galileo's further conclusion that these discoveries supported Copernicus's sun-centered model was more troubling. It threatened the established worldview and the authority of those who had embraced the old Ptolemaic system. Over the next 2 decades, Galileo entered into public debates and wrote dialogues arguing for the new astronomy. Eventually, this boldness brought him before the Inquisition. In 1633, under threat of severe punishment, Galileo was forced to recant his advocacy of heliocentrism. According to a famous but possibly apocryphal story, after he recanted, he muttered, "Eppur si muove." And yet, it moves, asserting that, recantation or not, Earth does move around the sun. Whether or not he actually said those words, the truth of the heliocentric system was by then becoming ever harder to deny. Galileo spent the final years of his life under house arrest, blind, but still mentally active, continuing to write about physics, Despite his personal suffering, the foundation had been laid. The telescope had forever changed astronomy, and Galileo's discoveries had given the Copernican model tangible, public evidence. No longer was heliocentrism just an elegant idea in a book. It was supported by observation, moons circling another planet, phases of Venus, a sun that rotated and was imperfect. The tide was turning. Even within the church and among learned men across Europe, the realization was dawning that Ptolemy's cosmology might be wrong. A new generation of astronomers continued Galileo's work with improved instruments, discovering, for example, additional moons and noticing subtle deviations in planetary orbits that begged for a new explanation. Meanwhile, Johannes Kepler, working hundreds of miles away in Germany, was solving the puzzle of planetary motion using the decades of observations made by Tycho Brahe. Kepler had been Tycho's assistant in Prague and inherited a treasure trove of the most accurate planetary data ever recorded, all gathered without a telescope, using giant protractors and sighting tools. Tycho had painstakingly plotted the positions of planets night after night, with particular focus on Mars, whose motion was the most puzzling. After Tycho's untimely death in 1601, Kepler took on the task of making sense of Mars's orbit, a problem that had baffled astronomers for centuries. Kepler tried and failed, again and again, to fit Mars's path to combinations of circular motions, as tradition insisted it must be. The data simply refused to line up with any arrangement of circles. Finally, Kepler broke with a millennia-old dogma. He abandoned the idea of perfect circular orbits and tried an oval shape, an ellipse. To his amazement, this change made everything fall into place. Mars's observed positions over the years traced an ellipse with the Sun at one focus. This breakthrough became Kepler's first law of planetary motion. Planets orbit the Sun in ellipses, not circles. Kepler soon discovered a second law as well. He found that as a planet moves along its orbit, it sweeps out equal areas in equal times. In practice, this means a planet travels faster when it is nearer the Sun and slower when it is farther from the Sun in its orbit. Kepler published these first two laws in 1609, fundamentally redefining celestial mechanics by showing that the planets' paths were not perfect circles, but ellipses governed by discernible rules. A decade later, in 1619, Kepler added a third law, connecting the motions of different planets in one elegant mathematical relationship. He discovered that the square of a planet's orbital period, the time it takes to complete one orbit of the Sun, is proportional to the cube of its average distance from the Sun. In simpler terms, the farther a planet is from the Sun, the more slowly it travels in its path, and not arbitrarily slower, but following a precise formula. This law hinted at a deep harmony in the solar system. Kepler called it the music of the spheres, imagining a cosmic symphony in which each planet's orbit was a musical note in the Sun's grand harmony. Kepler's laws, based on Tycho's data and his own genius for patterns, described the solar system's motions with unprecedented accuracy. Yet even Kepler did not know why the planets moved as they did. He had answered the question of how the planets move, but the underlying cause, the force, driving them, remained a mystery. That explanation would come later, from Isaac Newton. But by the early 17th century, thanks to Galileo's telescopic evidence and Kepler's mathematical laws, the heliocentric model had transformed from a controversial hypothesis into the foundation of a new understanding of the cosmos. The dawn of modern astronomy had truly arrived, a time when careful observation and mathematical reasoning together began to unlock the secrets of the heavens. The stage was now set for the next great insight, one that would tie together the motions of the heavens and the motions on Earth under a single, elegant theory. On a plague-haunted evening in the 1660s, a young Isaac Newton sat in the countryside of England, watching an apple fall from a tree. This simple observation sparked a profound question in his mind. Could the same force that pulled the apple to the ground also reach all the way to the moon? Newton, a brilliant yet reclusive thinker, set about formulating a revolutionary idea: that a single universal force governs the motion of both earthly objects and celestial bodies. By the late 17th century, Newton had developed 3 laws of motion and a law of universal gravitation, uniting the physics of the heavens and the earth. In one sweeping framework, he explained why planets orbit the sun and why the moon orbits Earth, as well as why an apple falls downward and not sideways. It was a moment of synthesis that scientists and philosophers had long dreamed of. The revelation that the cosmos is bound together by the same natural laws everywhere. Newton's laws of motion provided the foundation. He described how objects move and interact. A body remains in steady motion or at rest unless acted upon by a force, inertia. A force causes a change in motion proportional to the mass of an object, encapsulated in the equation F = ma. And for every action, there is an equal and opposite reaction. These simple principles could describe a cannonball's arc through the air or the orbit of the moon with equal precision. But it was Newton's insight into gravity that truly unveiled a universal harmony. He proposed that every mass in the universe attracts every other mass with a force that diminishes with the square of the distance between them. This was the law of universal gravitation. Using this law, Newton proved mathematically that the very same gravitational pull that causes an apple to drop from a branch will compel the moon to continually fall around Earth rather than fly off into space. In other words, the moon is forever falling toward Earth, but because it also has sideways motion, it falls around Earth and thus orbits. Gravity, Newton realized, is the invisible hand that guides the planets in their courses and choreographs the dance of moons and comets. It is a force that operates on Earth and in the heavens alike, binding the universe into one law-governed system. In 1687, Newton published his masterwork, the Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, known simply as the Principia. In it, he laid out his laws of motion and gravity and demonstrated that Kepler's laws of planetary motion were natural consequences of these deeper principles. The Principia showed that the elliptical orbits of planets, the swing of the moon around Earth, and even the path of a comet were all explicable by one universal law. It was a staggering achievement. Suddenly, the cosmos seemed knowable and orderly, as if a grand clockwork, previously veiled, had been revealed. Astronomers could now use Newton's equations to predict phenomena with unprecedented accuracy. The return of Halley's comet. Newton's friend Edmund Halley did exactly that, predicting the comet's return in 1758. The ebb and flow of ocean tides caused by the moon's gravity, or the slight perturbations in Saturn's motion due to Jupiter's pull. Celestial events no longer required separate explanations or the hand of capricious gods. They were all part of a single physical system. Newton's work completed the Copernican revolution. With a comprehensive physical explanation for why planets orbit as they do, the sun-centered model was no longer a mere geometric convenience but a dynamic reality governed by universal laws. In Newton's universe, the same physics applied everywhere. A stone tossed in the air on Earth and a planet orbiting the sun both obeyed the same principles of motion. This unity was inspiring and even spiritual to Newton's contemporaries. Many spoke of a clockwork universe, a grand mechanism created perhaps by a divine clockmaker, set in motion and left to run according to its natural laws. To Newton himself, uncovering gravity and motion was a way to glimpse the clockwork of God's creation. He humbly described his insights as thinking God's thoughts after him. The influence of Newton's discoveries on astronomy and science was immense. Future astronomers would use his mathematics to dive even deeper into the cosmos. In the centuries after Newton, his laws led to the discovery of new planets. For example, perturbations in Uranus's orbit led 19th century astronomers to predict and then find Neptune, lurking beyond the range of naked eye vision. Newton's framework also allowed an understanding of phenomena far beyond the solar system. The idea that the universe is governed by universal principles set the stage for all subsequent physics and astronomy. By the end of the 17th century, thanks to Newton, the cosmic dance of planets and moons was no longer a mystery choreographed by unseen spirits, but a predictable ballet ruled by gravity and motion. Humanity had discovered a universal harmony in nature, a set of laws that applied from an apple falling in an orchard in England to the planets swinging through the void. It was a triumph of human reason and observation, marking the true beginning of modern science's confidence in comprehending the cosmos. Newton's era closed a chapter in astronomy. The basic framework of the solar system and its governing laws were now understood. But even as Newton's achievements answered age-old questions, new ones emerged. What were the stars made of? How far away were they truly? Was the sun just one star among countless others? And what were those faint, cloud-like patches, nebulae, that telescopes were beginning to reveal in the night sky? As the 18th century turned to the 19th, astronomers stood ready to tackle these mysteries. They would do so with new tools and new physics, kicking off yet another revolution in our perception of the cosmos. By the dawn of the 19th century, astronomers had a solid grasp of the solar system's layout and the laws governing planetary motion. But the stars beyond remained mysterious lights, their distances, compositions, and natures unknown. Two new tools of that century would change that: the prism and the photographic plate. Through these, light itself would reveal the secrets of the stars, and the cosmos would be mapped on a scale never before imagined. One of the first breakthroughs came from dissecting starlight. In 1802, a British scientist noticed dark lines in the spectrum of sunlight when he spread it into a rainbow with a prism. Later, a German optician named Joseph von Fraunhofer mapped hundreds of these dark lines with precision. No one knew what they meant at first. It wasn't until 1859 that physicists Gustav Kirchhoff and Robert Bunsen in Heidelberg discovered the key. When they heated elements like sodium or hydrogen in a flame, they produced bright lines of color at specific wavelengths, a unique fingerprint for each element. Those same patterns of lines, seen as dark gaps against the sun's rainbow spectrum, meant those elements were present in the sun's outer layers, absorbing certain colors. Suddenly, the chemistry of the heavens opened up. Astronomers realized that the sun and stars were made of the same kinds of elements found on Earth. The iron in our blood, the calcium in our bones. These existed in the distant stars as well. Humanity learned that we share a common chemistry with the stars. This new science of spectroscopy, reading the coded light of stars, revealed astounding things. Helium, for example, was discovered in the sun's spectrum in 1868 during a solar eclipse, before it was found on Earth. It was named after Helios, the Greek sun god. By comparing stellar spectra, astronomers found that stars came in different types. Some were hotter, some cooler, each with its own spectral signature. Father Angelo Secchi in the 1860s began classifying stars into groups by their spectra, a first attempt at identifying stellar types and temperatures. Decades earlier, the philosopher Auguste Comte had declared that humans would never know what the stars are made of. Yet now they did. The stars were no longer just points of light. They were physical objects, composed of the same atoms as Earth, blazing at thousands of degrees, each with its light carrying a story across space. The prism and spectroscope became a cosmic cipher, allowing astronomers to decode starlight and read the chemistry of distant worlds. While the prism unveiled the star's composition, the photographic plate revolutionized how we recorded and discovered celestial objects. Before photography, astronomers had to rely on drawings and human vision, which could only see so much and left no permanent record beyond sketches. But in 1839, the invention of practical photography changed everything. In 1840, John W. Draper took the first photograph of the moon, capturing details of its surface on a fragile daguerreotype plate. Over the following decades, as photographic techniques improved, astronomers began attaching cameras to telescopes. Unlike the human eye, a photographic plate could collect light over long exposures, revealing faint stars and nebula invisible to the eye. In 1850, the star Vega was photographed at Harvard Observatory, the first photograph ever taken of a star, aside from the Sun. By the 1880s, astronomers like Henry Draper were taking long-exposure images of nebulae. Draper's photograph of the Orion Nebula in 1880 showed wisps of cosmic gas and starlight in a detail no eye could ever see. Suddenly, the universe was unveiling itself on glass plates. Those images could be studied, measured, and kept for posterity, allowing astronomers to make discoveries that no one could grasp in a single night at the eyepiece. Photography didn't just capture pretty pictures, it vastly expanded star catalogues and enabled new discoveries. With sensitive plates and ever larger telescopes, 19th century astronomers conducted ambitious surveys of the sky. They catalogued hundreds of thousands of stars, far beyond the few thousand visible to the naked eye. For example, German astronomer Friedrich Argelander and colleagues published the Bonner Durchmusterung in the 1860s, charting the positions and brightness of over 300,000 stars in the northern sky. Similar surveys extended to the southern skies. The sheer scale of the stellar universe was coming into focus. Once, humanity knew only the stars as unchanging pinpoints overhead. Now each could be recorded, its brightness measured, its position fixed on a map. By 1890, the Henry Draper catalogue, begun at Harvard College Observatory by a team that notably included several pioneering women astronomers, was classifying stars by their spectra. New variable stars were discovered on photographs, stars that mysteriously brightened and dimmed over time, hinting that physical changes and cycles were happening in distant suns. Bit by bit, the night sky was being quantified and understood in ways never before possible. Other 19th century breakthroughs further expanded our cosmic perspective. In 1838, astronomer Friedrich Bessel managed to measure the first reliable distance to a star, 61 Cygni, using parallax, the slight shift in a star's apparent position as Earth orbits the Sun. The angle he measured was tiny, but from it, Bessel calculated that 61 Cygni was over 10 light-years away, on the order of 100 trillion kilometers. This was stunning proof of the star's immense distances. It confirmed what Copernicus's followers had long suspected. If Earth's motion around the Sun produced no easily observed parallax in the stars, it was because the stars were incredibly far. Now at last, the void between the stars had a measurable scale. Meanwhile, other observers found new planets in our own solar system: Uranus in 1781 and Neptune in 1846, and discovered moons around those worlds, as well as numerous asteroids and comets. The inventory of the solar system was growing, and with it, our understanding of our cosmic neighborhood. By 1900, astronomers had measured the size of Earth's orbit, the astronomical unit, gauged the distance to a few of the nearest stars, and begun to suspect that the Sun was just one star among many in an enormous city of stars we call the Milky Way. As the 19th century drew to a close, astronomy had transformed into astrophysics, a science not only of where objects are, but what they are and how they move. The universe felt larger and more dynamic than ever. The Milky Way's misty band of light was now understood to be the combined glow of billions of distant stars within our galaxy. Whether the faint spiral nebulae observed in some telescopes were separate galaxies far beyond our own or nearby swirling clouds of gas was still debated, a question poised on the brink of an answer. The groundwork was laid for the next great steps. As the 20th century dawned, ever bigger telescopes and bold new physical theories were on the horizon. Questions about the true scale of the universe, the nature of those mysterious nebulae, and even the fundamental fabric of space and time were about to find dramatic answers. The story of the cosmos was far from complete. A new chapter of discovery was about to begin, built upon 4 centuries of astronomical progress. From the first sky watchers and the first myths to the sciences of spectra and photographic light, humanity stood at the threshold of deeper cosmic understanding, ready to take another giant leap in revealing the cosmos. For countless generations, humanity looked up at the night sky and found stories written in the stars. In the darkness above, our ancestors saw the campfires of gods and the silhouettes of great heroes. They whispered tales of creation and fate, comforted by the gentle rhythms of sun and moon. In time, these early myths and rituals laid the groundwork for something new. Beyond storytelling, a few began to seek patterns, to chart the movements of heaven itself, hoping to understand the cosmic order beneath the mystery. Under the warm night skies of ancient Mesopotamia, a priest stands atop a towering ziggurat of mud brick and stone. The air is still, and the world below sleeps, but above, the heavens are alive with shimmering lights. In silence, the priest gazes upward. One by one, familiar stars rise in their appointed places. A delicate sliver of the moon hangs low on the horizon. With a practiced eye, he notes the first appearance of a bright star just before dawn. By dawn's faint light, he marks a wet clay tablet with careful wedges, recording this heliacal rising. The stars return after its long absence in the sun's glare. It is more than an observation. It is a sacred duty. For the star-watching priests of Babylon, the night sky was a cosmic scripture written by the gods. Each star, each wandering planet, was a deity moving through the heavens and speaking in light. The planet Venus, shining brightly at dusk or dawn, was Inanna, Ishtar to the Babylonians, a goddess of love and war. Reddish Mars was Nergal, god of conflict. Golden Jupiter was Marduk, king of the heavens. To these priests, mapping the stars and planets was to chart the intentions of divine powers. The patterns above were omens and guidance, a cosmic order that mirrored the fate of kings and the prosperity of fields. So they kept vigil through the nights, their eyes tracing the slow dance of the wandering stars against the fixed constellations. By the glow of oil lamps, they filled tablets with star lists and observations. Over generations, a vast archive of celestial records grew in the libraries of clay. They noted when a faint glow of a star cluster first appeared in the east on a spring morning, or when an eclipse darkened the midday sun. They observed the intervals between lunar phases and the paths of the moon against background stars. Patterns emerged from the pages of night. The moon completed its cycle in just over 29 days. The sun returned to its starting point after about 12 cycles of the moon, and certain stars rose at the same time each year, heralding seasonal changes. In these observations lay the seeds of the first calendars and cosmic maps. The Babylonians divided the sky into 3 great pathways, corresponding to their chief gods, organizing the bewildering array of stars into a comprehensible scheme. They imagined the heavens as a dome arcing over the flat earth, divided into the path of Enlil in the north, Anu in the middle, and Ea in the south. Along the broad band where the sun, moon, and planets journeyed, they identified prominent constellations that marked the sun's yearly path. In time, they listed 12 constellations in this zodiac belt, giving us early forms of the signs we know today. There was the heavenly bull, the roaring lion, the scales, and the scorpion. Ancient patterns, later woven into Greek and modern star maps, though often renamed and reinterpreted. Each night's records helped them predict the next. In Babylon's bustling cities, beneath those same stars, kings and merchants awaited the priests' interpretations of the sky's portents. If a reddish star loomed bright in the east, conflict might be on the horizon. If the moon vanished unexpectedly, the gods could be warning of a coming calamity. Over centuries, these stargazers learned to anticipate some celestial events. They detected cycles. The moon's eclipses followed a pattern that repeated every 18 years or so. The restless dance of Venus as morning and evening star ran in an 8-year rhythm. With this knowledge, they could sometimes foretell an eclipse or the return of a brilliant comet, turning fearful unknowns into expected guests in the sky. So high were the stakes that when an ominous eclipse or alignment was foretold to threaten the king, the Babylonians did not sit idle. On such occasions, they would sometimes enthrone a proxy king, perhaps a minor noble or even a prisoner, while the real monarch withdrew into seclusion. The idea was that any celestial wrath would fall upon the substitute ruler. After a few days, when the heavens had calmed and the danger was deemed past, the true king would quietly resume the throne. This practice of the substitute king underscores how deeply the Mesopotamians believed the sky's drama was entwined with earthly fate. Yet even as they sought predictive power, their work carried a reverent wonder. Imagine a lone priest in those hours before dawn, perched high above the dark, sleeping streets of Babylon. He consults his star charts, clay tablets etched by his ancestors centuries before, and awaits the rising of a particular star that the records say should soon grace the horizon. In the east, the sky begins to pale. Then, just as predicted, a tiny point of light twinkles into being above the silhouette of distant palm trees. A gentle smile crosses his lips. The cosmos is in order. The star has returned on schedule. Rolling up his wool cloak against the morning chill, he offers a prayer of thanks to the sky. The great wheel of heaven turns as it should. For the Babylonians, to chart the heavens was to affirm that the world made sense, that the gods still presided over a consistent creation. Their astronomer priests were guardians of this cosmic order, keeping chaos at bay through careful attention and ritual. In their temples, they taught apprentices the secrets of reading the skies like a gigantic clock. They passed down star names and numbers, mathematical tools to calculate moonrises and planet positions. Using a counting system based on the sacred number 60, they devised methods to divide time and circles precisely, echoes of which persist today in our 60 minutes and 360 degrees. The patterns they recorded in clay became invaluable knowledge, surviving long after Babylon's own towers had crumbled back to dust. This early astronomy was not cold or detached. It was entwined with myth and meaning. Every measurement was also a meditation. Watching the planet Jupiter on its slow trek among the stars was communing with Marduk's influence. Tracking the crescent moon's return was celebrating the goddess Ishtar's light emerging from darkness. The skies were alive and aware, and by mapping them, the Babylonians felt they were participating in the divine drama. Through careful observation, they wove a tapestry of heaven and earth, time and eternity, science and spirituality. Their legacy would spread far beyond their fertile valley, carried by scholars and travelers to distant lands, inspiring other peoples to look upward and learn. Indeed, when Alexander the Great's conquests brought Greek scholars face to face with Babylon's star priests in the 4th century BCE, the Greeks were astonished by the archives of observations stretching back in time. A Babylonian priest named Berossus even travelled west to the island of Kos, where he is said to have taught the Greeks the Chaldean wisdom of the heavens. Thus, the meticulous records of Mesopotamia seeped into the wider world, planting seeds that would influence Hellenistic and later Islamic astronomy. As the millennia turned, this spark of systematic stargazing caught fire across cultures. From the land of Mesopotamia, knowledge flowed westward and eastward. Other ancient civilizations, with their own unique visions, would take up the quest of mapping the heavens. The human desire to understand the sky was only beginning, and along the Nile, under a different sky, another civilization was aligning its life, death, and monuments to the cosmos. Along the Nile, under a golden sun and starry nights, another ancient civilization bound its fate to the heavens. In Egypt, each day began with the triumphant rise of Ra, the sun, blazing over the eastern desert. His light spilled over the green banks of the Nile, bringing life to crops and warmth to stone temples. By dusk, as the sun descended westward, Egyptians believed it was swallowed by the sky goddess Nut, who would carry it through the darkness in her star-studded belly. Come dawn, Nut would give birth to the sun anew. This daily cycle of light and dark, death and rebirth, was the heartbeat of their world, a divine rhythm aligning earthly life with the cosmos above. To the people of the Nile, the sky was a grand stage where gods sailed and pharaohs found their eternal home. The sun was their supreme deity, and the pharaoh was often called the son of Ra, embodying the sun's power on earth. When a pharaoh died, elaborate rituals prepared him for a journey to the stars. Inside the dark chambers of pyramids and tombs, priests painted constellations on ceilings and carved spells into stone walls. These texts promised that the king would join the imperishable stars that circle nightly around the North Pole, never setting, never dying. In prayers, they imagined the departed ruler soaring among those undying lights, or sailing in the solar bark alongside Ra through the sky. Life and death were thus intimately linked with the celestial order. Not only did the Egyptians look to the sky for spiritual guidance, they also used it to govern daily life. Thousands of years ago, Egyptian priests noticed a striking yearly omen in the heavens. Just before the life-giving flood of the Nile arrived, the bright star Sirius, known to them as Sopdet, would reappear on the horizon at dawn after a long absence. On that summer morning, when Sirius first twinkled in the glow of daybreak, the priests proclaimed the new year. This heliacal rising of Sirius signalled that the Nile's floodwaters were imminent, ready to soak the parched fields. By aligning their calendar to this star, the Egyptians tied their agriculture to the cosmos. The rhythms of planting, harvest, and inundation were set to the celestial clock. Over time, they formalized one of the world's earliest solar calendars. It divided the year into 365 days, 3 seasons of 4 months each, plus a brief festival period to honor the gods as the year reset. Though simple by today's standards and lacking a leap year, this calendar served them for millennia, regulating everything from farm schedules to religious festivals. And always, Sirius remained the anchor, the heavenly herald of renewal. When the stars' timely rise matched their calendar predictions, it affirmed that all was in harmony. The sky, the river, and the kingdom were in tune. The Egyptians also mastered the art of orienting their monuments to celestial events. Perhaps nowhere is this more evident than at Giza, where giant pyramids of stone were constructed with astonishing precision. The sides of the Great Pyramid are almost perfectly aligned with the cardinal directions, north, south, east, and west, an achievement likely guided by careful observation of the stars. On clear nights, Egyptian surveyors could determine true north by watching the circling of stars around the celestial pole. By marking the point between the rotation paths of 2 bright stars, they found the north-south line and anchored their pyramid accordingly to mirror the order of the cosmos. Within that great pyramid run narrow shafts angled toward the heavens. Though their exact purpose is debated, many believe these channels were directed toward specific stars, significant in the pharaoh's journey. One narrow shaft on the pyramid's south side points toward the 3 stars of Orion's belt, part of a constellation the Egyptians identified as Osiris, their god of rebirth and afterlife. To their eyes, Orion himself was Osiris in the sky, and nearby, the star Sirius was Isis, Osiris's devoted wife. Night after night, as Orion rose and Sirius followed, the Egyptians saw a divine drama above. Isis pursuing her beloved Osiris across the heavens, a celestial echo of their cherished myths of resurrection. Another shaft aimed northward toward the never-setting stars near the pole, the imperishable ones that never vanished below the horizon. Through these openings, the spirit of the departed could ascend and mingle with the eternal lights, securing immortality in the sky. Far to the south, at Abu Simbel, colossal statues of Pharaoh Ramses II gaze eastward. In the depths of his temple, the sanctuary waits in darkness. But twice each year, at the dawn of a particular day, the rising sun's rays reach straight through the temple entrance, illuminating the inner chamber and the face of the king's statue within. In those brief minutes, the boundary between earth and sky dissolves, and the pharaoh is bathed in the sunlight of the gods. This magnificent solar alignment, timed to what are now late February and late October, was no accident, but a testament to the architect's celestial knowledge and the pharaoh's desire to be in harmony with the cosmos. The great temple of Karnak in Thebes offers another celestial spectacle. Its main axis was designed so that on the winter solstice, the shortest day of the year, the rising sun would send its first rays through the massive columns and gateways, all the way to the holiest shrine deep inside. On that morning, As the sun peaked over the horizon, its light would pierce the temple's sanctuary, illuminating the statue of Amun, the chief god, uniting heaven and earth in a single radiant beam. Such moments of alignment were powerful. They marked seasonal turning points and affirmed that the gods still smiled upon the kingdom. Even in more ordinary settings, the Egyptians wove astronomy into daily practice. Temple priests became skilled timekeepers, using simple instruments like the merket, a sighting rod with a plumb line, to track stars as they crossed the meridian each night. By observing the regular rise of particular star groups at set times, they could divide the dark hours into nightly hours. They named certain bright star groups deacons, using them to tell time during the night, much as sundials did by day. Water clocks dripped steadily in the silence of temple halls, calibrated by the stars overhead. In this way, they measured the hours of darkness as reliably as the sunlit hours, ensuring that rituals were performed at the proper cosmically ordained times. Even in death, the Egyptians sought comfort in the familiar stars. Inside tombs, ceilings were painted deep blue and studded with golden stars. Often the sky goddess Nut was depicted arching over the earth, swallowing the sun at dusk and birthing it at dawn, an eternal cosmic cycle to guide the deceased on their journey. Priests also painted tiny constellations, the deacons, along these ceilings. These were the star groups used to mark each hour of the night. By tracking the deacons, even a soul in the silent darkness of a tomb could sense the progression of time until dawn. On coffin lids, star clocks, and celestial diagrams provided a map of the heavens, complete with gods assigned to different hours of darkness. With such starry guides, the departed soul could navigate the afterlife, just as the living navigated the Nile by the sky. It was a comforting promise. The cosmic order that sustained life on Earth would also light the way in the world beyond. All these efforts stemmed from a desire to bring human life into harmony with the divine cosmos. The Egyptians saw patterns in the sky as reflections of Ma'at, the principle of cosmic order and balance that they strove to maintain in all things. So the layout of their cities, the timing of their festivals, the final resting places of their kings, all were aligned with celestial patterns to honor that order. A farmer tilled his field knowing the star of Isis, Sirius, would bring the flood on time. A priest lit incense at the moment when a certain star culminated, believing that was the precise hour the gods favored. A dying pharaoh closed his eyes for the last time, trusting his soul would fly up and join Orion, shining forever. Under the Egyptian sky, life, death, architecture, and time itself were bound tightly to the march of the heavens. On clear nights, as the Milky Way arched over the desert like a shimmering river of stars, one can imagine an Egyptian gazing upward in silent reverence. To them, that hazy band might have appeared as the celestial Nile, an echo of their own river in the sky. In their minds, the universe was a grand temple, and every glittering star was a lamp lit for eternity. In that enduring light, they found comfort and meaning. As Egypt's civilization flourished and then waned, much of its star wisdom was passed on or rediscovered by those who followed. The baton of astronomical knowledge travelled across the Mediterranean. Centuries later, under different skies, the Greeks would inherit some of this cosmic understanding and seek their own truths among the stars, transforming myth into mathematics in their quest for celestial harmony. Beneath the crystal-clear skies of the Aegean, the ancient Greeks, too, found their myths among the stars. on balmy summer nights, a family might sit under olive trees and point up at the patterns of light. There was a great hunter striding across the heavens, Orion, gleaming with a belt of 3 stars. Low on the horizon crawled a giant scorpion, the constellation Scorpius, which the Greeks said had stung Orion, driving him to his fate among the stars. In their folklore, the scorpion and the hunter eternally chase each other across the sky. When Scorpius rises, Orion hastens to set, fleeing the deadly creature. Elsewhere, they saw the figure of mighty Hercules kneeling, the proud Queen Cassiopeia sitting on her throne, and the winged horse Pegasus forever rising. Every group of stars became a story, a divine drama silhouetted in the night. The constellations we know by Greek names are a rich tapestry of such tales, passed down in poems and taught to children as part of their cultural heritage. Even beyond scholarly circles, star knowledge had practical value. Greek farmers and sailors kept an eye on the heavens for guidance. The poet Hesiod, around 700 BCE, offered advice to countrymen. When Orion and the dog star Sirius rise together at dawn, the heat of harvest time has arrived. When the Pleiades set at dusk, it's time to plough. Centuries later, the poet Aratus wrote his famous Phaenomena, a didactic poem mapping the constellations and their seasons, so that anyone could learn where each star rose and set. Through such works, the stars became a calendar and compass for ordinary people, woven into folklore and daily life. Yet the Greeks would also take a crucial further step. They sought not just stories in the stars, but principles. They invented the word cosmos to mean an orderly, harmonious universe. Theirs was a civilization that celebrated reason and inquiry, and in the sky they found an irresistible mystery that called for explanation. What made the sun blaze and wander? Why did the moon wax and wane? How did the distant stars move so predictably? Perhaps, some thought, there were hidden laws or symmetries guiding it all, like an eternal piece of music. By the 6th century BCE, philosophers in Ionia and beyond began to propose bold ideas. They moved away from seeing the cosmos purely as a realm of unpredictable gods, imagining instead a kind of cosmic machine governed by knowable rules. One early thinker, Thales of Miletus, is said to have predicted an eclipse, astonishing his contemporaries. Whether legend or not, it symbolized the new belief that the sky's phenomena were not random, but cyclical and comprehensible. Thales' student Anaximander speculated that the Earth floated in space, and that the sun, moon, and stars might be rings of fire encircling the world. These ideas were crude beginnings, but they opened the door to a more systematic astronomy. Perhaps the most influential were the Pythagoreans, followers of the philosopher Pythagoras. They believed deeply in the power of number and harmony, in the melodies of a lyre string and the proportions of a triangle. Pythagoreans saw eternal truths. To them, it seemed only natural that the cosmos itself was built on harmonious principles. They imagined that the distances of the planets corresponded to musical intervals, and that as the spheres swung around the Earth, they created a celestial music, the music of the spheres, too perfect and constant for human ears to hear. Pythagoras and his school taught that the Earth was not a flat disk, but a sphere, reasoning that the sphere was the most elegant and harmonious shape. They even toyed with the idea that Earth might not sit at the exact center of the cosmos, that perhaps it moved or rotated in tune with the celestial symphony. Radical thoughts not widely accepted for centuries, yet whispered among those early scholars. Out of such musings grew a more concrete science of astronomy. In Athens, Plato pondered the movements of the heavens and declared that the most perfect motion was the circle, since the gods would only use perfect forms. This insistence on circular, orderly motion set a challenge that would occupy sky watchers for generations: how to reconcile the actual wandering paths of planets with the ideal of uniform circles. Plato's student Eudoxus took up that challenge. He envisioned a series of transparent, nested spheres around Earth, each carrying a planet or stars, each rotating gently to produce the observed motions. With several spheres per planet, spinning at different speeds and tilts, Eudoxus managed to approximate the curious backward and forward dance of planets like Mars in the sky. It was a bold attempt to bring mathematics to the heavens, to literally draw the cosmos as a set of interlocking circles. Aristotle further refined the idea of celestial spheres, weaving it into a grand philosophical cosmology. To Aristotle, the Earth sat immobile at the centre, made of heavy elements like earth and water, while the heavens were a separate realm composed of ether, a divine substance. He taught that dozens of crystalline spheres carried the moon, sun, planets, and fixed stars, all turning in unison like a great orrery. He imagined unmoved movers, akin to divine intelligences or angels, imparting motion to these spheres from the outside, keeping the cosmic clock ticking. In Aristotle's universe, everything had its place: the imperfect, changeable earth below, and the perfect, eternal heavens above. This picture of a layered cosmos would hold sway for almost 2,000 years, deeply influencing later Roman and medieval thought. But Greek astronomy did not rest on pure speculation. It flourished through observation and measurement as well. In the port city of Alexandria, the intellectual jewel of the Hellenistic world, astronomers combined Greek theories with rich data and star lore inherited from Egyptians, Babylonians, and others. There, around 250 BCE, Aristarchus of Samos dared to compare the size of the Earth's shadow during a lunar eclipse to the size of the moon, deducing that the moon was much smaller than Earth and far closer. He also measured the sun's angle in the sky at 2 locations, a tricky feat that led him to realize the sun lay far beyond the moon and likely dwarfed the Earth in scale. In a leap of imagination, Aristarchus proposed a radical idea. Perhaps the sun, not the Earth, was the center of everything, and the Earth, like other planets, moved around it. This heliocentric theory was far ahead of its time and did not gain traction among his peers. But it showed how Greek thinkers were inching toward a more accurate cosmic layout. Around the same time, another Alexandrian scholar, Eratosthenes, achieved a feat just as remarkable in its elegance. He learned that at noon on the summer solstice, the sun shone straight down to the bottom of a deep well in the town of Syene, far up the Nile, meaning the sun was directly overhead there. In Alexandria, on the very same day and hour, he measured the shadow cast by a tall obelisk. The sun was not directly overhead in Alexandria. The obelisk cast a slight shadow. By comparing the length of the shadow to the height of the obelisk, Eratosthenes calculated the angle of the sun's rays. It was about 1/50th of a full circle. That difference in sun angle corresponded to the distance between the 2 cities. With this, Eratosthenes reasoned that the Earth's surface curved, and he was able to estimate the Earth's circumference with astonishing accuracy, all using simple observation and geometry under the open sky. The Earth, it turned out, was indeed a great sphere, as Pythagoreans had suspected, and now its vast size was measured. Greek stargazers also systematically charted the heavens. Around 150 BCE, Hipparchus of Nicaea set to work cataloguing the positions and brightness of over 1,000 stars. Working on the Isle of Rhodes, he compared his star maps to those of earlier observers and noticed something astonishing. The stars' positions were not fixed over centuries, but drifting very slightly. The constellation that once rose at the spring equinox now rose a little earlier in the year than it used to. From this, Hipparchus discovered the slow wobble of Earth's axis, a phenomenon now called the precession of the equinoxes. He measured it as a tiny shift, accumulating over long ages, and thereby revealed that even the seemingly constant heavens change on a grand timescale. The Greeks even attempted to capture the cosmos in machinery. In modern times, divers discovered an extraordinary bronze device in an ancient shipwreck near Antikythera, dating to the 2nd century BCE. Inside its corroded fragments were interlocking gears and dials, a mechanical sky calendar. This Antikythera mechanism, as it's now known, could predict eclipses and track the cycles of the moon and possibly the planets. It was essentially a clockwork model of the solar system, astonishing evidence that some Hellenistic artisans had transformed astronomical theory into precise engineering. Such a creation hints at how deeply the idea of a knowable, ordered cosmos had taken root, down to the crafting of instruments that mirrored the heavens. All these achievements laid the groundwork for the most comprehensive ancient model of the cosmos, crafted in the 2nd century CE by Claudius Ptolemy in Alexandria. Ptolemy gathered centuries of observations and wisdom into a great synthesis. In his treatise, later called the Almagest, he presented a detailed geocentric model where the Earth sat at the center and the Sun, Moon, and planets orbited it. But to match the observed motions, Ptolemy employed an ingenious system of circles upon circles. Each planet moved in a small circle, an epicycle, whose center in turn moved along a larger circle around Earth. These nested cycles allowed his model to predict planetary positions and even the timing of retrograde loops fairly well. It was a triumph of mathematical astronomy and became the definitive reference for the next 14 centuries. Alongside this, Ptolemy also wrote on astrology and the influences of the planets, reminding us that the line between science and mysticism remained blurred. To Ptolemy and his contemporaries, understanding the cosmos was both a practical and a philosophical pursuit. It helped navigate ships, create calendars, cast horoscopes, and ponder humanity's place in the grand design. By the end of the classical age, the Greeks had transformed the night sky from a canvas of myth into a subject of mathematics and philosophy. They left a legacy of star names, constellations, and a vision of a harmonious cosmos that would enchant scholars for generations. The idea that the universe was knowable and followed orderly principles, an idea born under Greek skies, became a cornerstone of the Western intellectual tradition. It set the stage for later cultures to question, to test, and eventually to revolutionize humanity's understanding of the heavens. Far beyond the Mediterranean, however, other eyes were also studying the stars and finding their own paths to wisdom. Through trade routes and migrations, Greek knowledge would eventually mingle with insights from distant lands. As the classical era gave way to new powers and faiths, a great exchange of astronomical ideas began to flow along the routes of silk and spice, uniting the star lore of India, China, the Arab world, and beyond into a rich, cosmic tapestry. Beneath the same stars that shone over Greece, caravans wound their way along the Silk Road, connecting west and east. In the dead of night, out on the high plains of Central Asia, a band of travelers might gather around a flickering fire. Above them, the Milky Way stretched like a silver banner, a river of light guiding them onward. These merchants and pilgrims came from many lands, some from the Mediterranean, some from Persia or India, others from distant China. As they sipped hot tea and rested, perhaps they spoke of the skies of their homelands. Each had stories to tell of how their people understood the glittering heavens. In exchanging these tales, They also exchanged knowledge, carrying ideas about the cosmos across thousands of miles. Long before such encounters, India had developed its own rich astronomical heritage. In ancient Vedic hymns, the sky was revered as the realm of Outer, the cosmic order. Early Indian priests observed the motions of the sun and moon to time their sacred rituals. Star watchers, known as nakshatra darsha, star seers, tracked the moon's passage through the sky against a backdrop of fixed stars. They divided the heavens into 27 or 28 sections, each marked by a particular star or cluster. These lunar mansions, or nakshatras, were used as a celestial calendar to guide sacrifices and festivals. For example, a full moon appearing in the section of the bright star Rohini, Aldebaran, heralded an auspicious time for certain rites. This star-dividing system predated the 12-sign zodiac and reflected a unique way of mapping the sky by the rhythm of the moon. Over time, Indian scholars compiled their observations into texts called Jyotisa, the science of light, which guided everything from agriculture to royal affairs. Eclipses especially fascinated and frightened them. Indian mythology imagined the phenomenon as the work of a cosmic demon. The story goes that the gods beheaded a trickster giant named Rahu after he stole a taste of the nectar of immortality. Rahu's bodiless head flew into the sky, where it eternally chases the sun and moon. Now and then it catches one, swallowing it and causing an eclipse, until the luminary slips out of its grasp. Despite this vivid myth, Indian astronomers learned to predict eclipses with increasing accuracy by observing their cycles. They knew, for instance, that eclipses often repeat in patterns, and could anticipate when the sun or moon would darken. They blended myth with mathematics, assuring people that though a dragon might swallow the sun, it would always release it on schedule. Indian astronomy reached impressive heights in the first millennium. Scholars like Aryabhata, born in the late 5th century, calculated the length of the year and the movements of planets with remarkable precision. He proposed that the daily rising and setting of the stars and sun could be explained by the rotation of the Earth on its axis, a startling insight for his time. Although Aryabhata still assumed the sun circled the Earth yearly, his idea of Earth spinning was a leap toward a heliocentric perspective. Later astronomers, such as Brahmagupta and Bhaskara, refined methods for calculating planetary positions and even spoke of gravitational attraction. Earth attracts that which rises, noted Brahmagupta, anticipating gravity's concept. They developed trigonometric techniques and sine tables to aid their computations, blending astronomy with pioneering mathematics. By the medieval era, Indian observatories dotted cityscapes, often atop temple complexes where priest astronomers could watch the skies. Using armillary rings and sighting rods, they tracked the timing of monsoons and the occurrence of eclipses. Indian calendars, complex blends of lunar months and solar years, guided the planting of rice and the dates of holy festivals. The stars and planets were also deeply woven into astrology, Jyotisha, which guided decisions from naming a child to crowning a king. Just as in Mesopotamia and Greece, the line between astronomy and astrology remained thin. Cosmic forces were seen as influencing human fate. Underlying it all was a conviction that by understanding the heavens, by reading the movements of celestial bodies, one could harmonize earthly life with the great cosmic dance. Knowledge, like monsoon rains, did not stay confined to one land. Indian star lore traveled abroad, mingling with ideas from Greece and Persia. Around the 8th century, scholars at the court of the Caliph in Baghdad translated an Indian astronomical treatise, the Sindind, derived from Sanskrit Siddhanta, into Arabic, bringing Sanskrit wisdom into the Islamic world. Indian methods for calculating eclipses and planetary motions enriched Islamic astronomy, just as earlier Greek ideas had. In turn, India absorbed influences from the West. The 12 zodiacal signs, familiar in Babylon and Greece, found their way into Indian astrological practice, blending with the older nakshatra system. By gazing at the same skies, these cultures were slowly synchronizing their cosmic maps. Farther east, under the vast skies of China, another ancient tradition had flourished. Chinese astronomers served their emperors by observing the heavens as vigilantly as other ministers monitored the kingdom. To the Chinese mind, the cosmos was a grand mirror of Earth. The emperor was the son of heaven, and any disruption in the sky, a comet, a nova, an eclipse, could be a heavenly commentary on his rule. Thus, charting the sky was not a mere academic pursuit, it was a matter of state. In records dating back over 3,000 years, we find meticulous notes of eclipses, comets with their fiery tails, and guest stars that suddenly appeared among the fixed stars, what we now recognize as novae or supernovae. One famous tale tells of two royal astronomers, Shi and Ho, charged with foretelling eclipses around 2000 BCE. They grew complacent, or so the story goes, and failed to predict a solar eclipse. The sky darkened unannounced, an alarming event that left the emperor furious. According to legend, these unfortunate astronomers paid with their lives for neglecting their duty. While the story may be embellished, it underscores how gravely the Chinese took celestial phenomena. In reality, Chinese astronomers did develop systematic eclipse prediction methods early on, using repeating cycles and later mathematical models to foresee when the heavenly dog might try to eat the sun. During eclipses, people would gather to bang drums and gongs, trying to scare away whatever monster was attacking the sky, until the sun's light returned. The Chinese mapped the stars in their own unique way. Rather than the large constellations of Mesopotamia or Greece, they divided the sky into many smaller asterisms, over 100 patterns, including the great celestial regions of the azure dragon of the east, the white tiger of the west, the black tortoise of the north, and the vermilion bird of the south. They recognized a band of the sky through which the sun, moon, and planets traveled, similar to the zodiac, but they split it into 28 lunar lodges or mansions that loosely corresponded to the Indian nakshatras. These served as markers for the moon's nightly progress and were key in their lunisolar calendar. The calendar itself, in China, was a marvel of astronomy and politics combined. Emperors instituted calendar reforms to assert their legitimacy, and astronomers worked to reconcile the lunar months with the solar year. They observed solstices and equinoxes to keep the seasons in tune, inserting extra months when needed to prevent the calendar from drifting far off the solar schedule. By the Han Dynasty, scholars like Zhang Heng built elaborate devices, bronze celestial globes and armillary spheres to model the sky, water clocks to measure time, and even an early seismoscope to detect distant earthquakes, all part of the quest to understand heaven and Earth's interplay. Chinese stargazers were careful observers of the wandering stars, planets, as well. They noted conjunctions and rare gatherings of planets, interpreting them as omens. A close approach of Jupiter and Saturn, for example, might be recorded as a portent of change in the imperial house. Comets, with their sudden apparition and sweeping tails, were described as broom stars, thought to sweep away the old order. Their appearance often linked to the fall of emperors or the rise of new dynasties. One of the most famous records comes from the year 1054, when Chinese astronomers observed a brilliant new star in the sky, visible even in daylight for weeks. They called it a guest star. Today we know it as the supernova that created the Crab Nebula, one of the few supernovae in history recorded in detail by any culture. Over the centuries, Chinese astronomy grew ever more precise. In the Tang and Song dynasties, imperial observatories were established, featuring towering armillary instruments and precise sighting tubes. Astronomers like Yi Xing in the 8th century devised more accurate calendars, even incorporating ideas from Indian astronomy brought by Buddhist scholars. In the Ming era, the ancient observatory in Beijing was equipped with finely crafted bronze instruments, later admired by visiting Jesuit missionaries. Through all these developments, Chinese scholars maintained copious star catalogues and maps. One surviving star map, painted on silk from the Tang era, shows constellations with remarkable accuracy and detail, evidence of a tradition that valued recording the night sky in enduring form. While China and India built their wisdom largely independently, by the Middle Ages, a new centre of astronomical learning rose that eagerly gathered knowledge from all quarters: the Islamic world. After the rise of Islam in the 7th century, a vast empire spanning from Spain to Persia became the conduit for Greek, Indian, and Persian astronomy to merge and flourish. Early caliphs in Baghdad set up the famous House of Wisdom, where scholars of many lands translated texts and exchanged ideas under the patronage of enlightened rulers. Ptolemy's great compilation, the Almagest, was rendered into Arabic and studied intensively. Indian star tables, the Sindind, were translated as well, as were Persian treatises. With this rich inheritance, Islamic astronomers embarked on their own observations under the clear desert skies. In the 9th and 10th centuries, luminaries like Al-Khwarizmi and Al-Battani refined existing star catalogues and astronomical tables. They measured the length of the year and the tilt of Earth's axis with exquisite care, improving on the values given by the Greeks. Al-Battani observed the sun's apparent motion and noted slight changes in its speed, refining the understanding of the solar orbit. He also recorded the shifting point of the sun's closest approach to Earth, what we call perihelion, over time. Meanwhile, other scholars focused on instrumentation. They perfected the astrolabe, a handheld model of the sky in brass, which could tell time by the stars or help calculate prayer times and the direction of Mecca. Across the Islamic realms, observatories were established to systematically watch the heavens. In the 13th century, the astronomer Nasir al-Din al-Tusi built a grand observatory at Maraga in Persia, equipped with large sighting devices and precise quadrants. There, he and his team re-examined Ptolemaic models, trying to resolve discrepancies between theory and observation. Al-Tusi devised a clever mathematical trick, now known as the Tusi couple, which could produce a small oscillation from the sum of two circular motions. This innovation allowed for more accurate modelling of planetary paths and would later inspire European astronomers during the Renaissance. In far-off Samarkand, in the 15th century, the Timurid prince Ulugh Beg erected another great observatory. He installed a massive marble sextant, reputedly 40 meters across, carved along a hill to precisely measure star positions. Ulugh Beg, though a ruler, was also a passionate astronomer. He compiled a new star catalogue with over 1,000 entries, updating ancient coordinates with observations so precise that many of his star positions were as accurate as those measured by European astronomers 2 centuries later. Tragically, Ulugh Beg's scientific pursuits earned him enemies at court, and he was assassinated. But his star catalogue survived, a testament to his dedication. Islamic astronomers also gave us many of the star names still in use. As they translated Greek works, they preserved or coined names like Aldebaran, Arabic for the follower, trailing the Pleiades cluster, Betelgeuse, likely from Ibn al-Jawza, the armpit of Orion, and Altair, from Altair, the flying eagle. These names whisper the legacy of medieval stargazers each time we point out a star. They also developed new terminology. Words such as zenith, from Arabic samt, meaning direction, and azimuth, from al-sumut, the plural of samt, became part of astronomy's vocabulary. Even algorithm harks back to al-Khwarizmi, reflecting the mathematical bent of these scholars. Amid their quest for knowledge, the astronomers of the Islamic Golden Age never entirely separated science from spirit. Many were devout, seeing their work as deciphering the signs of Allah's creation. The Quran itself encourages believers to reflect on the stars and planets as signs of divine wisdom. This theological backdrop provided both motivation and a moral framework for scientific inquiry. The night sky, to these scholars, was a grand manuscript written by the Creator. Each calculation or observation was a way to understand the beautiful language in which it was penned. Through translations and the movement of people, Islamic astronomy eventually bridged into medieval Europe. By the 12th and 13th centuries, scholars in Spain and Italy were eagerly translating Arabic texts, which themselves preserved Greek and Indian wisdom, into Latin. The works of al-Battani, al-Sufi, and many others became known in the West, sparking new growth in Europe's understanding of the heavens. The Silk Road of the Stars had connected diverse cultures into a continuous chain of learning. Each civilization, Indian, Chinese, Arabian, contributed its insights, and in turn gained new perspectives from its neighbours. By the late medieval period, humanity's knowledge of the sky was a rich tapestry woven from many traditions. Even as knowledge flowed freely across Europe, Africa, and Asia, the far side of the world was not silent under the stars. Far beyond the networks of the Old World, great civilizations in the Americas nurtured their own astronomy, untouched by the East. In the jungles and high plateaus, peoples like the Maya and the Aztecs built massive temples and carved stone calendars to track the heavens' cycles with astonishing sophistication. And on the open ocean, seafaring navigators from distant islands learned to read the night sky as a map, finding their way across vast, unmarked waters by the stars alone. Truly, the human connection to the cosmos was universal, arising independently wherever people looked up to the celestial lights. Under the thick canopy of a tropical forest, the pre-dawn air is cool and laden with mist. Atop a steep pyramid of stone, a Mayan priest stands silent, awaiting a sign from the sky. As the eastern horizon grows light, a single star, the morning star, Venus, pierces the twilight. The priest watches intently. To the Maya, Venus is no mere pinprick of light, but a powerful omen. Its rising or setting can herald times of peace or war, the fates of kings, or the timing of sacred rites. Satisfied by the planet's position, the priest descends the temple steps. Today's ceremonies, from the lighting of incense to the greetings of the sun, will be timed to the cosmic schedule. In ancient Mesoamerica, the heavens and the earth moved together as one. The Maya, whose cities flourished in the jungles and mountains of what we now call Central America, were masters of cosmic timekeeping. They observed the cycles of the sun, moon, and planets with a devotion that rivaled any culture on Earth. Over centuries, they refined multiple calendars, interlocking them like gears to measure both mundane and mythic time. One calendar of 365 days tracked the solar year, the cycle of planting and harvest, while another sacred calendar of 260 days cycled through combinations of numbers and day names, believed to influence the fortune of each day. Together, they formed a calendar round of 52 years. To the Maya, a 52-year period was like a century of destiny, after which the calendars reset to their starting alignment. We can imagine the significance of such a moment. As one calendar round closed and another began, there was both anticipation and anxiety. Would the world renew itself safely for another cycle? The skies held answers. On the evening when the calendars rolled over, Mayan sky watchers looked to the heavens for reassurance. If the Pleiades star cluster glittered at the zenith and Venus rose propitiously, it was a sign that the cosmic order remained intact. Fires would be lit anew, marking the commencement of the next 52-year era. In these moments, time itself felt like a sacred circle, clicking back to the start, guided by the stars. Beyond the calendar round, the Maya conceived of even greater cycles using their long count, an extraordinary timeline spanning thousands of years. They recorded dates deep in the past and far in the future, anchoring mythic events in a grand cosmic history. According to Maya reckoning, the current world age began on a date they equate to 3114 BCE. They believed that every 5,125-year cycle, the universe would undergo renewal. This wasn't an apocalyptic end, but a transformation, akin to the turning of a very great wheel. By inscribing these cycles on stelae and codices, the Maya proclaimed that the story of the cosmos and the story of their people were inseparable. They saw themselves as actors in a divine narrative written in the language of stars and time. Such knowledge did not remain abstract. It was built into the very cities and temples of Mesoamerica. Many Maya ceremonial centers were aligned with celestial events. At the city of Tikal, temples are oriented so that on the equinox, the sun rises precisely over specific structures when viewed from particular sightlines. In Uaxactun, a complex of structures marks the solstices. Stand on one temple, and you see the sun rise over another temple on the longest and shortest days of the year. At Uxmal, the pyramid of the magician is said to align with the movements of Venus. And most famously, at Chichen Itza, the grand pyramid called El Castillo, the temple of Kukulkan, plays host to a striking spectacle each equinox. As the sun sets on those days, the angle of its light along the pyramid's stepped terraces creates the illusion of a serpent made of sunlight slithering down the northern stairway. The effect draws thousands of onlookers even today. To the ancient Maya, this was Kukulkan, the feathered serpent deity returning to Earth, a brilliant union of architecture, astronomy, and myth. Mayan astronomers observed and recorded with astounding accuracy. In the surviving Maya codices, accordion-fold books of bark paper filled with hieroglyphs, we find tables that predict solar and lunar eclipses and chart the exact rise and set dates of Venus over many years. They knew that Venus, as the morning star, would disappear for a time and then reappear as the evening star. And they tallied this cycle as 584 days, nearly exactly right. With their arithmetic, often using base 20 and including the concept of zero, they could calculate these celestial rhythms for centuries ahead. This knowledge was held by an elite priesthood and passed down through generations, cloaked in religious significance. To know the workings of the sky was to have insight into the intentions of the gods and the timing of fate. The Aztecs, who rose to power in the Valley of Mexico many centuries after the heyday of the Maya, inherited much of this astronomical tradition and made it their own. In their capital city, Tenochtitlan, built on an island in a great lake, the Aztecs constructed the Templo Mayor, a twin pyramid at the city's heart. One temple atop it was dedicated to Huitzilopochtli, the god of the sun and war, and the other to Tlaloc, the rain god. On the equinox, standing at a certain point, an observer would see the rising sun align between these two sanctuaries, uniting the powers of sun and rain for the new season's fertility. The Aztecs, too, watched the skies ardently. They followed the cycles of Venus with particular concern, as it was tied to a central myth of their people. They believed the current age, the fifth sun, was a precarious era that required human devotion to keep it alive. Every 52 years, when the calendar round completed, the Aztecs performed the new fire ceremony to prevent the end of the world. As the old cycle closed, all fires throughout the land were extinguished, plunging the empire into darkness. Priests ascended a sacred mountain and waited for the Pleiades to appear at the zenith around midnight. If the stars were in their expected place, it meant the cosmos had not ceased. With great relief, they kindled a new fire, sometimes, according to accounts, in the chest cavity of a sacrificial victim, though the grim details were cloaked in ritual. From this single flame, runners fanned out to relight every hearth in the valley, symbolizing the renewal of life and sanction of another 52 years of sunrises. Violent as some of their rites were, the Aztecs' aim was cosmic balance. They saw the sun as a weary deity, one that needed the sustenance of sacrifice to continue its journey across the sky. Each dawn was, in their eyes, a victory wrested from the jaws of darkness by the offerings made the day before. In their cosmology, the crimson sunrise was tinged with the very life force they had returned to the heavens. It is a sobering and profound illustration of how far humans would go to feel connected and essential to the cosmic order. Elsewhere in the Americas, other peoples also aligned their lives to the sky. The Inca of South America, for example, set up pillars around their capital of Cusco to mark where the sun rose and set at solstices, creating a solar calendar against the mountain horizons. The Inca even discerned figures in the Milky Way's dark lanes of stars. Llamas, serpents, and other animals outlined by the black voids against the starry glow. Celestial shapes drawn not by light, but by shadow. In North America, some plains tribes built medicine wheels, rings of stones on the ground, that appear to mark sunrise points on the summer solstice and certain star risings, suggesting open sky observatories used for ceremony and calendar making. The drive to orient oneself in time and space with the help of the heavens was universal. Whether in dense Yucatan jungles, high Andean valleys, or broad prairie lands, people sought alignments between earth and sky to give structure and meaning to their world. Even on the open ocean, far from any landmark, the stars became trusted guides. Long before modern navigation instruments, Polynesian wayfinders set sail across the Pacific, navigating to tiny islands over immense distances with only nature's signs to lead them. By day, they watched the sun's arc and the flight of birds, and by night, they turned to the stars. They knew the rising and setting points of dozens of stars and constellations at different times of year. In their canoes, without maps or compasses, they carried a mental star compass, an understanding that at a given time of year, a specific bright star would rise at a certain point on the horizon, leading the way to an intended island. For instance, to voyage north, a navigator might sail toward the place where Hokulea, Arcturus, climbs the sky. To head south, they might follow the line of the Southern Cross when it tilts above the waves. They felt the patterns of ocean swells and the directions of winds as well. But it was the sky that provided the ultimate framework. Generation after generation, Polynesian navigators memorized these star paths, often training from youth by lying on their backs beneath the night sky, visualizing voyages as sequences of rising and setting stars. In essence, they extended the concept of a map into the dome of the heavens itself. Navigators in other cultures, too, relied on starry beacons. In the northern hemisphere, sailors learned to find Polaris, the North Star, fixed in its celestial place, to guide their way. On deserts and savannas, traders trekked by the stars when daytime heat made travel impossible, steering caravans across trackless sands. For centuries, the night sky was humanity's universal compass. The great explorers of the European age of sail, Columbus, Magellan, and others, still depended on the heavens, using instruments like the astrolabe and cross-staff to measure the height of the sun or North Star above the horizon and fix their position at sea. In a way, they were heirs to a tradition as old as the first humans who dared venture beyond the sight of home. If you know the stars, you can always find your way. Under every sky, whether navigating waves or sowing fields or erecting temples, humankind looked above for orientation and assurance. The heavens offered a constant backdrop against which we could measure our transient lives and uncertain journeys. By the end of the 15th century, as Polynesians still traversed open seas by starlight and Aztec priests watched for omens in the dawn, another chapter in humanity's relationship with the sky was about to unfold across the ocean in Europe. There, scholars and mystics stood on the threshold of profound change. But in the medieval centuries before that leap, Europe too had its era of cosmic contemplation, a time of faith, seeking understanding amid the stars, when astronomy mingled with theology, and every comet or eclipse could stir both awe and apprehension. In medieval Europe, under the dim light of candles and the eternal light of faith, the cosmos was a sacred and well-ordered kingdom. Imagine a scholar monk in a stone monastery around the year 1200. He sits hunched at a wooden desk, an ancient manuscript open before him, its pages filled with Latin script and diagrams of concentric circles. In his hand, he holds a small astrolabe, a bronze disc etched with star patterns and sliding scales. Through a narrow window above, the night sky sparkles with winter stars. From time to time, he peers out and aligns the astrolabe with Polaris to gauge the hour. The faint starlight and the steady drip of wax from his candle are his only illumination. In this quiet moment, the scholar contemplates the heavens as understood in his age, a series of crystalline spheres encircling the earth, each one carrying celestial bodies in their ordained paths, all part of a divine design. To the medieval mind, the structure of the cosmos was as much theological as it was physical. Drawing on the legacy of Aristotle and Ptolemy, scholars taught that the earth was the motionless center of creation. Above it rose the successive spheres of the 7 known planets: the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn, each embedded in a transparent shell rotating at its own pace. Beyond them lay the 8th sphere of fixed stars, containing all the constellations. Beyond that, a crystalline sphere to account for the precession of the equinoxes. And farther still, the primum mobile, the first moved sphere that imparted motion to all those within it. Finally, enveloping everything, was the Empyrean, the highest heaven, the realm of God and the angels, suffusing the cosmos with divine light. This layered universe was finite yet majestic, like a great celestial clockwork designed by the Creator. Every component had its purpose, and nothing was arbitrary. It was an image that provided comfort and meaning. Humanity, at the center of it all, was not an insignificant speck, but the focus of God's plan. The stars and planets, in their perfect circles, were thought to influence the imperfect world below. Medieval astrologers, often learned clerics themselves, cast horoscopes to advise kings on matters of state and to guide physicians in balancing the humours of the body. Astrology fit within the Christian worldview, as long as it acknowledged God's ultimate sovereignty. The heavens could incline fate, but not irrevocably bind it, as scholastics would say. Still, nearly everyone assumed that celestial events could mirror or foreshadow events on Earth. A bright comet might be seen as a divine warning of upheaval. A lunar eclipse at an unexpected hour could send villagers rushing to churches to pray, fearing that some demon or dragon was trying to devour the moon. Not all celestial observations inspired fear. The calendar of the church itself depended on astronomy. Each year, monk mathematicians calculated the timing of Easter, the first Sunday after the first full moon following the spring equinox, a task requiring careful observation of the seasons and lunar cycle. Throughout monasteries, the ringing of bells for prayers, the divine office hours, originally followed the sun and stars before mechanical clocks took over. Some monastic communities used sundials by day and special star clocks by night to mark the sacred hours of matins and lauds. In this way, the rhythms of heaven guided the rhythms of prayer and work, keeping earthly life in sync with the perceived harmony of the cosmos. Medieval universities included astronomy in the curriculum as one of the 7 liberal arts, part of the quadrivium alongside arithmetic, geometry, and music. Students in Paris or Bologna around the 13th century might listen to lectures on the sphere of the world, a popular textbook summarizing the Ptolemaic cosmos. They learned to use astrolabes to find the altitude of Polaris, and thereby their latitude, or to determine the time of night from the position of certain bright stars. They memorized the order of the planets and their crystalline spheres, reciting lists of zodiac constellations in Latin. But this was not taught as a cold, technical science. It was imbued with a sense of divine order. Professors spoke of the music of the spheres, an idea inherited from antiquity, suggesting that the planets in their courses sang in silent harmony. Everything in the heavens was interconnected with Earth by sympathy or correspondence, part of a grand chain of being that led from the lowliest earthly creatures up through the stars and planets to the angels, and ultimately to God. Literature and art of the medieval period reflect this enchanted view of the sky. The epic poem, The Divine Comedy, by Dante Alighieri, written in the early 14th century, takes the reader on a journey through the cosmos, as it was then imagined. Dante ascends through the 9 celestial spheres, meeting blessed souls and angelic intelligences who move those spheres. He finds the love of God manifesting as a blinding light beyond the highest heaven, moving the sun and other stars by its sheer goodness. Such imagery was not mere poetry. It encapsulated how people earnestly perceived the universe. They truly believed the stars were imbued with spiritual influence, that angels guided the turning of planets, and that beyond the farthest star lay the ultimate source of light and love that gave all things motion and purpose. Around the same era, the abbess Hildegard of Bingen experienced vivid visions of the cosmos that she set down in illuminated manuscripts. In one vision, she saw the universe like a cosmic egg, Earth at the center, encased by layer upon layer of celestial spheres, all glowing with the fire of the Holy Spirit. Her drawings depict zodiac rings and winds turning the firmament, a mystical, breathing cosmos where material and spiritual realms intertwined. Such depictions, half art and half astronomy, were another way medieval minds tried to grasp the structure of creation through faith and vision. Beneath this cosmic canopy, medieval scholars also pursued more hands-on celestial inquiries. Some, like the English monk Roger Bacon, advocated in the 13th century for empirical observation and even imagined fantastical inventions like flying machines or magnifying lenses to better study creation. Others meticulously recorded celestial events in chronicles. A new star that unexpectedly appeared in 1572, after the medieval period, now known as Tycho's supernova, shattered the belief in an unchanging heaven. A century earlier, in 1456, Halley's comet, though not yet called that, blazed across the sky. Pope Calixtus III even ordered special prayers to beseech God to deliver Europe from any evil the comet might herald. Each unusual event in the sky was folded into the medieval narrative of a universe rich with meaning. A comet could be a sign of divine displeasure or a harbinger of great change. A lunar halo might spark fears of bad weather or war. The sky's messages were mysterious, yet seldom ignored. Alchemy and astrology, twin arts of the occult, flourished alongside more orthodox learning. Alchemists laboured to turn base metals into gold and sought the elixir of life, guided by a philosophy that saw correspondences between the heavens and the earth. 7 classical metals were linked to the 7 planetary spheres. Gold belonged to the sun, silver to the moon, copper to Venus, iron to Mars, and so on. An alchemist in his hidden workshop might consult an astrological almanac to choose the right hour for a distillation, believing that a conjunction of planets or a particular phase of the moon could influence the subtle properties of matter. Though chemistry and astronomy today stand apart from mysticism, in medieval times they were entwined in a single quest to understand the mysteries of God's creation. A physician would draw upon astrological charts to diagnose illness and time treatments. A devout astronomer like Johannes Kepler, who bridged the late Renaissance, saw no conflict in casting horoscopes while searching for divine mathematical harmonies in planetary orbits. On dark nights, when a meteoric fireball streaked across the sky, or the aurora borealis shimmered unexpectedly far to the south, communities often responded with awe and piety. People lit candles before saint statues or held processions, hoping to avert whatever ill such signs might portend. Comets were described in chronicles as long-haired stars or fiery swords hanging over the world, and could kindle dread of war or plague. In 1066, a brilliant comet, now known to be Halley's, was recorded by observers across Europe and even depicted on the Bayeux tapestry. To the English of that year, it seemed to herald the Norman conquest, an omen of doom. To the Normans, perhaps, a sign from God of victory. Such events reminded medieval people that they lived under a watching heaven, and that history and destiny were tied to the motions above. For all the worries celestial omens could bring, there was deep comfort in the regularity of the stars. Every night, no matter the turmoil on earth, the constellations wheeled on in their ancient patterns. The Big Dipper still pointed the way to the North Star. Orion still strode across the winter sky. The Pleiades still rose before dawn in their season. This dependable cosmic rotation reassured medieval souls that a higher order prevailed. They might not understand all the heaven's secrets, but they trusted that God did, and that was enough. The careful preservation of ancient knowledge and incremental improvements by Islamic and European scholars kept the flame of astronomy alive through the Middle Ages, awaiting the next great leap. Unbeknownst to the people of those times, that leap was on its way. As the 15th century turned to the 16th, a few curious minds began to question the old models. Voyages across the globe were expanding the known world, and strange new stars seen from the southern hemisphere hinted that maybe the cosmos was larger and more complex than Aristotle had taught. The stage was quietly being set for a dramatic transformation. In a cathedral city in Poland, a canon named Copernicus studied ancient texts and started to toy with a sun-centered idea. In time, his thoughts, and the observations of those who followed, would crack the crystalline sphere of tradition wide open. But to the medieval stargazer finishing his prayers on a cold night, the notion that Earth could be just another planet was almost unthinkable. He would snuff out his candle and climb the stairs to the dormitory, believing firmly that tomorrow the sun would rise again, as it always did, carried by divine ordinance, and that the structure of the universe would hold as reliably as the turning of the pages in his cherished books. The medieval sky slowly brightens into a Renaissance dawn. As the stars fade with morning light, we leave this world of armillary spheres and angelic harmonies, knowing that a new chapter awaits. It will be a chapter of bold exploration and profound revelation, when long-held truths are upended by the simple act of gazing through a new kind of glass, and the universe unfolds in ways even the ancients never imagined. The cosmos holds its breath, poised on the cusp of change, as a new age of discovery prepares to unveil the mysteries that our ancestors could only dream of. For thousands of years, the cosmic order seemed clear and comforting. Earth, solid and unmoving, lay at the center of all things, while the sun, moon, and wandering planets circled around us in perfect spheres. The stars were thought to be fixed in a crystalline firmament, the outermost shell of a finite universe. In this geocentric cosmos, humanity appeared to occupy a special place. Ancient philosophers like Aristotle taught that the heavens beyond the moon were unchanging and divine, composed of ethereal perfection. Ptolemy later refined this picture with complex epicycles to explain the planet's motions, keeping Earth at the privileged center. Under these ancient skies, people gazed upward and felt the universe revolving around them by design. By the Renaissance, however, cracks were forming in this Earth-centered view. Scholars rediscovered hints from antiquity that challenged the status quo. In the 3rd century BCE, a Greek astronomer named Aristarchus had boldly proposed that it was the sun at the center, with Earth in motion around it. His idea was dismissed and forgotten for centuries. But in the 16th century, a quiet Polish cleric named Nicholas Copernicus revived this radical concept. Copernicus spent long years observing the heavens and poring over astronomical tables. He grew convinced that the majestic dance of the planets would be more elegantly explained if the sun, not Earth, sat in the center of the known universe. Copernicus worked slowly and cautiously, aware that moving Earth from the center of creation would be a profound upheaval. In 1543, as he neared the end of his life, he published his great treatise on the revolutions of the heavenly spheres. According to law, a freshly printed copy reached Copernicus on his deathbed, allowing him a final glimpse of his legacy. In those pages, the cosmos was redrawn. The sun shone at the center. Earth became just one of several planets circling it, and Earth itself spun on its axis every day. The scheme beautifully explained why planets sometimes appeared to move backwards, retrograde motion. It was an illusion created as Earth overtook them in its orbit. But this new heliocentric model also shattered the familiar order. If Earth moved, where was our special status? If the sun reigned at the center, how vast must the universe be to make the stars appear unmoving? Copernicus's bold model expanded the cosmos, and humbled our planet's role within it. The initial reaction to the Copernican system was muted. To many scholars, it was a clever mathematical calculation rather than a depiction of reality. It lacked solid proof and contradicted common sense and scripture. After all, if Earth were hurtling through space, why did things not fly off its surface? And if we spun, why didn't we feel it? Copernicus had answers. He suggested that the scale of the universe was so great that Earth's motion made an imperceptible difference in the stars' positions, and that physics on a moving Earth would operate much as it does on a stationary one. Still, the idea was unsettling. Over decades, a few astronomers were won over by the heliocentric model's simplicity. Others, like the influential Tycho Brahe, proposed hybrid arrangements to avoid putting Earth in motion. It would take further evidence and time to truly ignite the Copernican revolution. That evidence would come from new eyes gazing at the skies, armed with a groundbreaking invention, the telescope. In the early 17th century, the next step in understanding our place in the cosmos came not from theory alone, but from direct observation. In 1609, an Italian mathematician named Galileo Galilei heard rumours of a new device invented in the Netherlands, a spyglass that could make distant objects appear closer. Galileo crafted his own improved version of this instrument, the first astronomical telescope, and pointed it at the night sky. What he witnessed through that slender tube would forever change our view of the universe. Galileo's first target was the moon. To the naked eye, the moon had always appeared as a smooth, glowing disk. But through the telescope, it sprang into detailed reality. Galileo saw dark shadows and bright regions. He realized the moon's surface was uneven, marked by mountains, valleys, and craters. Just like Earth's terrain, the lunar landscape was rugged. This shattered the Aristotelian notion that celestial bodies were perfect, unblemished spheres. The moon was another world, more like Earth than anyone had imagined, with light and shadow revealing a stark topography. The divide between heaven and Earth began to blur. Turning his telescope to the planets, Galileo observed Jupiter, the largest of them. On January nights in 1610, he noticed 3 little starlets near Jupiter, arranged in a line. They seemed to move relative to Jupiter over hours and days. Soon, a 4th appeared. Galileo realized these were not background stars, but moons orbiting Jupiter. He had discovered the 4 largest moons of Jupiter, now known as Io, Europa, Ganymede, and Callisto. This was astonishing evidence. Here was a miniature planetary system. Not everything revolved around Earth. These moons clearly circled Jupiter. It was a vivid demonstration that Copernicus could be right. Celestial bodies could orbit centers other than Earth. Galileo then observed Venus, the planet that, from Earth's perspective, shows phases like the moon's. Over months, he watched Venus transform from a slender glowing crescent to a broader, almost full disk, and back again. In Ptolemy's Earth-centered model, such a sequence of phases would not occur, because Venus's epicycle kept it near Earth between us and the Sun. But in the Sun-centered model, Venus orbits the Sun and displays the full range of phases as its position relative to Earth changes. Galileo's observations of Venus matched the heliocentric prediction exactly. When Venus swings around the far side of the Sun, we see it nearly fully lit, though smaller in apparent size. And when it comes between Earth and the Sun, we see it as a large crescent. This was compelling evidence that Venus circled the Sun. Galileo's telescope revealed other surprises. He found that the Sun itself had imperfections. By projecting the Sun's image onto a flat surface, he observed dark spots that slowly shifted in position and shape. These sunspots would appear and vanish over days, indicating that the sun rotated and that it was not the eternal, immaculate light many imagined. Galileo also noticed that Saturn looked peculiar through his telescope, as if it had ears or handles. Though his instrument wasn't powerful enough to discern the rings, he knew something was unusual about it. And gazing into the soft glow of the Milky Way, Galileo discovered it was composed of countless faint stars, previously invisible. The universe suddenly seemed far more populous and expansive than human eyes alone could perceive. Each of Galileo's discoveries chipped away at the old worldview. The moon was Earth-like, the sun was blemished and rotating, Jupiter had its own moons, Venus revolved around the sun, and the heavens held far more stars than anyone had suspected. Galileo, once a professor of mathematics, with a gift for experiment and demonstration, understood the significance of these findings. He became an outspoken champion of the Copernican system. Writing in Italian rather than Latin, he made his work accessible to a broad audience. His 1610 treatise, The Starry Messenger, astonished readers with news of mountains on the moon and moons around Jupiter. He followed it with letters and essays, laying out evidence that nature, through the telescope, was revealing a sun-centered plan. But Galileo's revelations brought him into conflict with powerful forces. The idea of an Earth in motion challenged not only academic tradition, but also religious doctrine. In 1616, the Catholic Church declared the Copernican view of the cosmos false and contrary to Scripture. Galileo was warned not to teach or defend it. For a time he remained prudent, focusing on other research. Yet he never truly abandoned the truth he had seen. In 1632, believing he had found a way to discuss the heliocentric idea diplomatically, Galileo published his dialogue concerning the two chief world systems. It was written as a conversation among three characters: an open-minded interlocutor, a proponent of Copernicus, and a defender of Ptolemy. Though the work purported to present both sides, the logic and evidence for the sun-centered system clearly won out in the dialogue's debates. The book was widely read and admired, but it angered church authorities who felt mocked by its thinly veiled critiques. Galileo was summoned to Rome to face the Inquisition once more. In 1633, the nearly 70-year-old Galileo stood trial. Under threat of severe punishment, he recanted his support for Copernican theory. He declared Earth static at the universe's center, a statement he knew was false. According to legend, after his forced confession, he muttered defiantly, "Eppur si muove." And yet, it moves. Whether myth or truth, that phrase has come to symbolize the triumph of evidence over authority. The Inquisition imposed house arrest on Galileo for life. He spent his final years confined to his villa in Arcetri, near Florence, where, despite blindness and isolation, he continued to write. It was there he completed 2 new sciences, summarizing his pioneering work on motion and the strength of materials, which was spirited out of Italy for publication. Galileo died in 1642, blind and still under house arrest. He did not live to see the Church lift the ban on Copernican ideas. That would come centuries later. But by the time of his passing, the evidence he unveiled had already permeated scientific circles. The torch of discovery was passing to a new generation. Fittingly, in that same year of 1642, far to the north in England, Isaac Newton was born. It would be Newton who took the questions Galileo left behind. Questions of how things move and why planets stay in their orbits, and answer them in a way that would forever change science and cement the understanding of a heliocentric cosmos. Isaac Newton came into the world as Galileo's was leaving it, Newton would go on to answer many of the questions that Copernicus, Kepler, and Galileo had raised. In the mid-17th century, science was still piecing together the puzzle of planetary motion. Johannes Kepler, using Tycho Brahe's meticulous observations, had found that planets move in ellipses, not perfect circles, and he formulated precise laws describing their speeds and distances. Yet, why should the planets follow those paths? What force governed their motion around the sun? It was a mystery waiting for a solution. Newton's moment of insight arrived in his early 20s. In 1665, as plague swept through England, Newton, then a student at Cambridge, retreated to his family farm in Woolsthorpe. Away from lectures and bustling city life, his mind ranged freely. It's here that the famous story takes place. Newton observing an apple fall from a tree. Whether the apple actually struck him or simply dropped nearby, the sight set him pondering. Why do objects fall straight down? What force pulls the apple to the ground? And could that same force extend all the way to the moon? Newton imagined the moon orbiting Earth as a kind of projectile, perpetually falling around Earth rather than into it. This was the germ of a revolutionary idea. The force of gravity that makes apples drop might also be the force that holds the moon in orbit. Over the next 2 decades, Newton developed the mathematical tools, including calculus, and conducted experiments that would enable him to formalize his insights. He established 3 laws of motion, principles that describe how objects move and interact. These laws explained inertia, why an object in motion stays in motion unless acted on, how forces change motion, and how actions create reactions. And crucially, Newton formulated the law of universal gravitation. Every particle of matter in the universe attracts every other particle, with a force proportional to their masses and inversely proportional to the square of the distance between them. It was a simple formula with profound consequences. Using this law, Newton could explain why planets follow Kepler's elliptical orbits. The inverse square attraction to the Sun naturally produces such paths. In 1687, urged on by his friend Edmund Halley, Newton published his masterpiece, Philosophia Naturalis Principia Mathematica, often known simply as the Principia. In this work, written in austere Latin and dense with geometry, he laid out the mathematical principles underlying motion and gravity. It was perhaps the single greatest scientific book ever published. The Principia demonstrated that the same gravitational force causing an apple to fall also governs the moon's orbit and the orbits of planets. Newton showed how to calculate the motions of celestial bodies, how gravity diminishes with distance, and how the interactions of multiple bodies produce slight perturbations, as in the case of Jupiter and Saturn tugging at each other. The heavens and earth were unified under one cosmic law. The impact of Newton's work was immense. Within his lifetime, and in the generations after, the Principia transformed our understanding of the cosmos into something quantifiable and predictive. Eclipses could be forecast centuries ahead. The return of Halley's comet in 1758, predicted by Halley based on Newton's laws, dramatically confirmed that Newtonian mechanics held sway even over the long orbits of comets. Later, in 1846, a discrepancy in Uranus's orbit led astronomers to apply Newton's gravity to predict another planet beyond it. When Neptune was found almost exactly where it had been predicted to be, it was seen as a resounding victory for Newtonian theory. The universe, it seemed, was a grand mechanism running on discoverable laws. Following Newton, many thinkers came to view the universe as a kind of clockwork. The phrase clockwork universe captured the idea of a cosmos so orderly and governed by physical laws that, given complete knowledge of initial conditions, one could foresee every future outcome. Space was seen as an absolute, unchanging stage, and time as a universal, steady flow, a cosmic clock ticking uniformly everywhere. God, or nature, had set this clockwork in motion, and now it ran its course with mathematical precision. This worldview, born of Newton's triumphs, imbued the 18th and 19th centuries with a strong sense of optimism about human reason and the power of science to eventually know all the fundamentals of how the world works. For over 2 centuries, Newton's framework reigned supreme. It guided explorers across uncharted seas using celestial navigation, underpinned the engineering of the Industrial Revolution, and explained the orbits of planets and moons with incredible accuracy. But as precise and all-encompassing as Newtonian physics seemed, nature still harbored subtle anomalies. One nagging issue was the orbit of Mercury, the closest planet to the Sun. Mercury's elliptical orbit slowly precessed, rotated, over time. While Newton's laws, accounting for tugs from other planets, explained most of this perihelion precession, there remained a small discrepancy that resisted explanation. It was as if Mercury felt a little extra nudge from something unseen. By the late 19th century, other cracks in the classical picture had begun to show. Experiments with light and electromagnetism revealed puzzles. For instance, the speed of light appeared constant, regardless of the Earth's motion through space, a result that defied intuition. And scientists like Max Planck and Niels Bohr were uncovering the quantum world, where energy came in discrete packets and certainty gave way to probabilities. Physics was approaching a crossroads. The stage was set for another paradigm shift. Just as Copernicus had displaced Earth from the center, and Newton had united heaven and earth under gravity, now Einstein would arrive to reshape our concepts of space, time, and gravity themselves. A new revolution was at hand, one that would once again upend our understanding of the cosmos. At the turn of the 20th century, physics stood on the brink of a profound transformation. Albert Einstein, a young patent clerk with a head full of ideas, became the agent of that change. In 1905, Einstein's Annus Mirabilis, Miracle Year, he published a series of papers that upended classical conceptions. One introduced the special theory of relativity. Einstein began with a simple postulate. The laws of physics and the speed of light should appear the same to all observers moving at constant velocity. From this, astonishing consequences followed. Time, which Newton had assumed flowed uniformly for everyone, turned out to be relative. If one observer moved at a high speed, relative to another, their clocks would no longer agree. The moving observer's time would run slower, a phenomenon later confirmed by precise atomic clocks on fast-moving planes. Lengths would contract along the direction of motion as well. And mass and energy were revealed to be two sides of one coin, related by E equals mc2. In practical terms, this meant a small amount of mass could be converted into a tremendous amount of energy, a principle that explained, for example, the energy source of stars and later enabled nuclear power on Earth. Special relativity forced humans to accept that simultaneity, the notion of now, can differ for observers in motion relative to each other. Space and time were not absolute backdrops, but interwoven and flexible. Einstein didn't stop there. He turned to the puzzle of gravity. Newton's theory of gravity worked extremely well. Yet it depicted gravity as a force acting at a distance through space, and it assumed time and space were absolute. Einstein suspected there was a deeper truth. He mused on thought experiments. Imagine being in an elevator in freefall. You'd float weightlessly, indistinguishable from being in empty space far from any gravity. This equivalence between freefall and the absence of gravity hinted that gravity might not be a pull from afar, but rather something inherent to space itself. Over roughly a decade of intense work, Einstein developed his general theory of relativity, presenting it in late 1915. General relativity proposed that mass and energy tell spacetime how to curve, and the curvature of spacetime tells objects how to move. In other words, gravity is not a force that reaches across space, but the result of objects moving along the curves and slopes in a warping of space and time. This idea was revolutionary. According to general relativity, Earth orbits the Sun, not because the Sun exerts a mysterious long-range force, but because Earth is following the curved geometry of space-time that the Sun's mass creates around it. Picture a heavy bowling ball, the Sun, placed on a trampoline, space-time. It creates a dip, and a smaller ball, Earth, rolling nearby, will spiral around the bowling ball within the depression. It's an imperfect analogy, as real space is three-dimensional and includes time, but it conveys the concept. Gravity emerges from geometry. General relativity made predictions that differed slightly from Newton's gravity. One was the bending of light by gravity. A beam of starlight passing near the Sun should deflect, since space-time is curved by the Sun. Another was the precise amount of Mercury's orbital precession, which Einstein's equations duly calculated, matching the tiny excess drift that Newton's theory couldn't account for. In 1919, a total solar eclipse gave scientists a chance to test Einstein's bold claims. During the eclipse, the Sun's blinding light was blocked, allowing astronomers to observe stars in the sky near the Sun's edge. The British astronomer Arthur Eddington led an expedition to measure the positions of those stars. Sure enough, the stars appeared slightly shifted from where they normally would be, indicating that their light had bent while skimming past the Sun, just as Einstein's theory predicted. When the news broke, Einstein became a global celebrity almost overnight. Here was a new, mind-bending picture of reality, verified by experiment. Einstein's general relativity had other dramatic implications. It predicted that time runs slower in stronger gravitational fields. A clock on a mountain will tick a bit faster than a clock at sea level, a difference measurable with today's technology. It also implied that the universe's fabric could vibrate. Gravitational waves would ripple out from massive bodies accelerating, rather like how a jiggling charge radiates electromagnetic waves. And lurking in the math were solutions that described black holes, regions of space-time so warped that they form a bottomless well, a place where time effectively stops, and all paths lead inward to a singularity. At first, black holes seemed so extreme that many doubted they would actually form in nature. Einstein himself was skeptical of physical black holes. But later theorists, like Carl Schwarzschild, who found the first black hole solution, and Subrahmanyan Chandrasekhar, showed that under reasonable conditions, such as a massive star's collapse, nothing forbids their creation. They remained hypothetical for decades, but as we know now, they do exist. General relativity didn't only reshape local understanding of gravity, it reshaped cosmology itself. In 1917, Einstein applied his equations to the universe as a whole. To his surprise, the equations suggested that the cosmos could not be static. It had to be either expanding or contracting. At that time, the common wisdom, and Einstein's own inclination, was that the universe was eternal and unchanging on the largest scale. To reconcile his theory with a static universe, Einstein introduced the cosmological constant, essentially a repulsive term that could counteract gravity at large scales and hold the universe in a stable size. He later called this addition his biggest blunder, after observations proved the universe was indeed expanding, though ironically, the concept of a cosmological constant would reappear in a different guise with dark energy. The evidence for an expanding universe came in the 1920s. American astronomer Edwin Hubble, observing myriad spiral nebulae, discovered that these were actually other galaxies, vast star systems far outside our own. He then found that the light from these galaxies was redshifted, stretched to longer wavelengths, and that the farther a galaxy was, the greater its redshift. This meant the galaxies were flying away from us, and more distant ones were receding faster. In 1929, Hubble published his findings, establishing that the universe was expanding uniformly. This was a paradigm-shaking revelation. If we imagine running the cosmic film in reverse, at some point in the past, all those galaxies would have been much closer together. The logical conclusion was that the universe had a beginning, a moment when it was extremely hot, dense, and compact, from which it expanded. Georges Lemaitre, a Belgian priest and physicist, had already theorized such a primeval atom explosion, what we now call the Big Bang. Hubble's data gave that idea a huge boost. Further supporting the Big Bang model was the later discovery of the cosmic microwave background, CMB, radiation in 1965. Arno Penzias and Robert Wilson, using a microwave antenna in New Jersey, stumbled upon a persistent background hiss coming from all directions in the sky. It turned out to be the faint afterglow of the hot, early universe, now cooled to just a few degrees above absolute zero, and stretched to microwave wavelengths after billions of years of expansion. This CMB was precisely what Big Bang theorists had predicted would be left behind if the universe began in a fiery burst. The discovery of this primordial light convinced nearly all scientists that the Big Bang was the correct description of our cosmic origin. Einstein did not directly contribute to these later cosmological developments. He initially missed predicting the expansion, and by the time the CMB was found, he had passed away. But his framework of general relativity was the foundation upon which modern cosmology was built. After Einstein, the universe was understood to be dynamic and evolving, a dramatic departure from the eternal, unchanging cosmos many had once assumed. He lived to see the early evidence of expansion and reportedly acknowledged that removing the cosmological constant might have allowed him to predict it. Einstein spent his later years pursuing a unified field theory, attempting to merge gravity with electromagnetism in a single mathematical framework. This goal eluded him, and indeed remains one of the great quests of physics today. Uniting general relativity, which handles the grand scale of gravity, with quantum mechanics, which rules the subatomic realm. It's a challenge for future Einsteins. By the time Einstein died in 1955, he had changed the landscape of science. He reminded us that even the most basic assumptions about time, space, and mass could be wrong, and that we must be willing to see the universe with new eyes. General relativity has since been confirmed in countless ways, from the slight bending of light by galaxies forming Einstein rings, to the time dilation measured by GPS satellites, to the recent detection of gravitational waves. Yet, for all it explains, Einstein's legacy also includes new mysteries he himself didn't foresee. It's to those mysteries, dark matter, dark energy, black holes, that astronomy turned in the latter 20th century. as we strove to fill in the remaining blank spaces in our picture of the cosmos. Moving into the later 20th century and beyond, astronomers peeled back more layers of the universe and encountered new puzzles that continue to baffle and intrigue. Perhaps the most profound mysteries revolve around two invisible yet dominant components: dark matter and dark energy. These terms stand for our current ignorance about most of what the cosmos is made of. The story of dark matter begins as far back as the 1930s. An astronomer named Fritz Zwicky, studying the Coma cluster of galaxies, noticed that the galaxies were moving so fast that they should have flown apart if the only thing holding them together was the gravity of the visible stars in the cluster. He proposed there must be dunkel materia, dark matter, providing extra gravitational glue. At the time, few paid attention. But in the 1970s, Vera Rubin, observing how stars rotate around the centers of spiral galaxies, found something astonishing. In galaxy after galaxy, stars far from the center were orbiting just as fast as stars nearer in. According to Newtonian physics and the visible mass, those outer stars should have been moving more slowly. Rubin's work implied that something unseen was adding gravitational pull in the outskirts of galaxies. It was as though each galaxy was embedded in a hidden halo of mass that kept the outer stars bound. This was strong evidence that a lot of matter in the universe is invisible. Further evidence accumulated. Clusters of galaxies showed gravitational effects too large for the visible matter alone. The way light from distant objects was bent, gravitational lensing, by galaxy clusters indicated more mass than we could see. Simulations of the universe's formation only matched observations when a big component of dark matter was included. Today, we think dark matter makes up about 27% of the universe's energy matter content. For comparison, normal matter is only about 5%. Dark matter doesn't emit light or energy that we can detect. That's why we call it dark. It might be some new kind of particle outside the standard set of particles we know. Physicists worldwide have built underground detectors, hoping to catch a rare interaction of dark matter particles with ordinary matter. But so far, these have yielded no definitive detections. Yet the indirect evidence of dark matter is overwhelming. It acts like an invisible scaffolding across the cosmos. Galaxies form and grow within halos of dark matter, and its gravity governs the motions we observe on large scales. While dark matter's nature remains unknown, another even stranger discovery was made in the late 1990s that has reshaped our understanding of cosmic fate: the discovery of dark energy. Two independent teams of astronomers were measuring the brightness of distant Type Ia supernovae, exploding stars used as standard candles, to see how the universe's expansion has changed over time. To their surprise, the supernovae appeared fainter than expected, as if they were farther away than our models predicted. The only reasonable explanation was that the expansion of the universe is accelerating. Instead of gravity slowing down the expansion, some mysterious repulsive force was speeding it up. This was an astonishing result. It's as if, on the grandest scale, gravity, from matter, is losing to a kind of anti-gravity effect. We named whatever is driving this acceleration dark energy. It's called dark because we don't see it directly and don't yet know what it is. In Einstein's equations of general relativity, a cosmological constant can produce this effect. Essentially, an energy inherent to empty space that doesn't dilute as the universe expands. Dark energy could be Einstein's cosmological constant in action, or it could be something else entirely, perhaps a new field, or a dynamic energy associated with space. What we do know is that observations of the cosmic microwave background and the distribution of galaxies suggest dark energy accounts for roughly 68% of the universe's total content. Combined with dark matter's 27%, that leaves just 5% for everything else. All the atoms in stars, planets, gas, dust, and living beings. This realization is humbling. All that we have seen, countless galaxies, each brimming with billions of stars, is the tip of the cosmic iceberg. The vast majority of the cosmos comes to us only through whispers of gravity and the distant effects on light, not through direct sight or touch. In a sense, after centuries of discovery, we find ourselves in a new dark age, but a promising one, where the darkness is a frontier of potential knowledge. Solving the riddles of dark matter and dark energy is one of the great challenges of 21st century science. It will likely require physics beyond what we currently know, possibly new particles or new laws. Apart from these unseen influences, astronomers in the modern era have also confirmed some of the more dramatic predictions of Einstein's theory. Black holes, once considered purely theoretical, have been observed indirectly and their effects measured. We talked about how stars in our galaxy orbit an unseen massive object at the center. That object is a black hole, with about 4 million times the Sun's mass. In 2015, scientists detected gravitational waves for the first time, using the LIGO detector. These faint ripples in spacetime came from two black holes merging together in a distant galaxy. For a brief moment, during that merger, the power output in gravitational waves was more than all the light from all the stars in the observable universe. LIGO's exquisite instruments picked up the stretching and squeezing of space as the wave passed through Earth, a distance change smaller than a proton's width, and yet unmistakable. It was as if we had heard the universe speak in a new language, the language of gravity. Since then, many more gravitational wave events have been recorded, including crashes of black holes and neutron stars. Each detection is a new kind of observation, giving us ears to complement our eyes on the cosmos. And in 2019 came an image that once would have been deemed impossible, a direct picture of a black hole's immediate surroundings. The Event Horizon Telescope collaboration combined radio telescopes across the globe to form an Earth-sized virtual dish. They set their sights on the supermassive black hole in galaxy M87, 55 million light-years away. The result was the now famous image of a glowing orange ring, light from hot gas swirling just outside the black hole's event horizon, surrounding a dark shadow where the black hole itself resides. It was a spectacular confirmation that these enigmatic objects are real and behave as general relativity predicts. As we gather this new data, the cosmos continues to astonish. We learn of neutron stars so dense a teaspoon of their material would weigh billions of tons, of exoplanets with skies and climates unlike anything on Earth, some with twin suns, others possibly with ruby rains, of galaxies colliding and merging in slow dances over eons. We've mapped the afterglow of creation and found the whisper of quantum physics in the cooling of that glow. Yet for every answer, new questions emerge. What caused the Big Bang? Are there perhaps other universes beyond our own? What happens to information that falls into a black hole? How will the universe end? With a bang, a crunch, a rip, or an eternal whimper as stars gradually fade out? Facing these questions, we feel the same sense of wonder that our ancestors did when they looked up and only dimly understood what they saw. We've come so far, from thinking the stars were campfires of the gods to realizing they are distant suns, from believing Earth was the center of creation to seeing it as a tiny world in an unfathomably vast expanse, from picturing heaven as a fixed sphere to detecting waves in spacetime itself. And yet, as far as we've journeyed, we are still at the shore of a cosmic ocean, with great uncharted waters before us. This is a hopeful realization, because mystery is the wellspring of discovery. Each generation, armed with new tools and ideas, sails a little farther. And as we turn our gaze now from the mysteries of matter and energy to the mysteries of life and destiny, we carry with us the humble knowledge that there is infinitely more to learn. For as long as people have gazed at the stars, they have wondered, are we alone? What other wonders might exist among those distant lights? In ancient times, myths peopled the skies with gods and heroes. But as our understanding grew, the question of life beyond Earth became a scientific and imaginative pursuit. By the late 19th and early 20th centuries, writers of speculative fiction were dreaming up voyages to the moon and adventures on Mars or Venus. H.G. Wells imagined Martians visiting Earth with hostile intent in the War of the Worlds, while Edgar Rice Burroughs wrote of a hero journeying to a dying Mars, which he called Barsoom, and finding civilizations there. These early tales reflected both our hopes and fears about extraterrestrial life. At the time, some astronomers thought they saw straight lines on Mars, misinterpreted as canals built by intelligent beings, and Venus, eternally hidden beneath clouds, was fancifully thought to perhaps harbour steamy jungles. Such ideas, though later disproved, kept alive the possibility that the universe might be teeming with life in one form or another. The dawn of the space age turned many of those dreams into reality, at least in part. In 1957, the Soviet Union launched Sputnik, the first artificial satellite, a polished metal sphere that circled Earth and sent back a beeping signal. Humanity had touched space. In 1961, Yuri Gagarin became the first human to orbit Earth, returning with the simple yet profound observation, "I see Earth. It is so beautiful." For the first time, a person looked down on all of humanity at once, not divided by borders, but united on a single blue planet. This new perspective was transformative, both scientifically and philosophically. As rockets carried our eyes and instruments farther, science fiction also blossomed on screens and pages, fueled by these real achievements. It was as if our collective imagination and collective effort were propelling each other forward. The pinnacle of human space exploration, so far, came on July 20th, 1969, when Neil Armstrong and Buzz Aldrin set foot on the moon. The world watched in awe and wonder as grainy black and white images showed Armstrong descending the ladder of the lunar module and uttering, "That's one small step for a man, one giant leap for mankind." Those footprints on the moon symbolized more than a technological triumph. They represented a species momentarily breaking free of its home world. Standing on the grey dust of another celestial body, and looking up at a sky without a blue earth filling it, was, as Armstrong later said, beautiful desolation. The Apollo astronauts brought back rock samples and a lasting gift for all humanity. A view of Earth from the moon that showed our world as a fragile oasis in space, without political boundaries, a solitary home that we all share. After the Apollo moon landings, human exploration receded closer to home. No person has been beyond low Earth orbit since 1972. But in place of humans, we sent emissaries, robots that do not tire or need life support. These mechanical explorers have extended our reach to every corner of the solar system. We have landed probes on Venus, revealing a hellscape of heat and pressure, and on Mars, finding ancient riverbeds and the chemical signs of a once habitable environment. We've visited Jupiter and Saturn and their moons. The Galileo probe dropped a capsule into Jupiter's clouds. The Cassini spacecraft orbited Saturn for 13 years, sending back breathtaking images of its rings and moons. Huygens, piggybacking on Cassini, parachuted onto the surface of Titan, Saturn's largest moon, in 2005, showing us a misty orange sky above a landscape of icy rocks and methane rivers. We've sent craft to the edges of the Sun's influence. Voyager 1 and 2, launched in 1977, have now passed into interstellar space, still faintly beaming back data as they wander the galaxy. Along the way, Voyager 2 visited Uranus and Neptune, the only craft ever to do so, gifting us the only close-up images of those distant blue-green giants and their moons. One of the most poetic gestures in exploration came when Voyager 1, upon completing its tour of the outer planets, turned its camera back toward Earth at the request of Carl Sagan. It took a picture from 3.7 billion miles away. In that photograph, Earth appears as a tiny, pale blue dot suspended in a sunbeam. Sagan wrote movingly about this image, pointing out that everyone you love, everyone you know, everyone you ever heard of, lived out their lives on that mote of dust. It underscored how small and precious our world is in the vast darkness. Such perspectives, offered by space exploration, resonate deeply. They remind us that despite our differences, we share a common home. As our robots explored, we also began seriously searching for life beyond Earth. We now know that in our solar system, Earth is the only planet with complex life, but there are tantalizing hints that simpler life might have gained a foothold elsewhere. Mars, for instance, had liquid water on its surface billions of years ago. Lakes, rivers, perhaps even an ocean in the north. Could Martian microbes have evolved in that wetter, warmer past? We have yet to find direct evidence, but Mars today still has water ice and likely subsurface brines, and upcoming missions plan to bring back Martian rock samples to scour for ancient fossils or chemical biosignatures. Further out, Jupiter's moon Europa and Saturn's moon Enceladus both hide global oceans beneath their icy crusts. Enceladus even vents plumes of water vapor into space like a whale spouting. Cassini flew through these plumes and detected organic molecules. These moons have heat from tidal flexing, water, and chemistry, raising the exciting possibility that if life can exist in the deep oceans of Earth around hydrothermal vents, maybe it can also exist in those alien oceans. Beyond our solar system, the question, "Are we alone?" took a major step from speculation toward data with the discovery of exoplanets. In 1992 came the first confirmed detection of planets orbiting another star, in that case a pulsar, a rather exotic environment. By 1995, the first exoplanet around a sun-like star was found, and then the floodgates opened. Especially in the last decade, thanks to missions like the Kepler Space Telescope, we have discovered thousands of exoplanets. We found planets around all types of stars, from tiny red dwarfs to big bright suns. We found systems with multiple planets, some in orbits so close to their star that a year lasts only days, others at distances far beyond that of Pluto. Perhaps most thrilling, we found a number of roughly Earth-sized planets in the habitable zones of their stars, the region where temperatures might allow liquid water to exist on a planet's surface. One such planet orbits our nearest stellar neighbour, Proxima Centauri. It's slightly larger than Earth and within the habitable zone of its dim red star. We don't yet know if it has an atmosphere or water, but its discovery makes the idea of Earth-like worlds seem much more tangible. With each new exoplanet discovery, our perspective on life's possibilities broadens. We're on the cusp of being able to analyze exoplanet atmospheres for signs of life. Things like an unusual mix of gases, oxygen alongside methane, for instance, that could indicate biological activity. The James Webb Space Telescope, launched in 2021, has already started probing some exoplanet atmospheres, and future missions might directly image Earth-like planets around nearby stars. It's a difficult task, akin to spotting a firefly next to a floodlight from miles away. But engineers are devising clever ways to block the star's light and isolate the planet's faint glow. In the meantime, SETI continues to quietly listen for artificial radio or optical signals that might be beacons from intelligent civilizations. The universe has been mostly radio silent so far, aside from natural cosmic noise. If other technologically capable beings exist in our galaxy, they either aren't transmitting in ways we can detect, or we haven't been listening long enough, or they are very rare. Some thinkers ponder the great filter concept. Perhaps life is common, but intelligent life is exceedingly rare or short-lived, which would explain the silence. Others suggest we might not recognize a signal even if it's there, due to differences in technology or understanding. For now, we have no evidence of alien intelligence. But the absence of evidence isn't evidence of absence. The search goes on, driven by the profound implications a single hello from the stars would carry. Even if we don't hear from ET tomorrow, humanity is not sitting idle. We dream of travelling farther ourselves. After Apollo, there is renewed interest in the moon. Plans are afoot to send astronauts back to the moon to establish a sustained presence, perhaps a lunar base or a station orbiting the moon that could serve as a gateway for further exploration. The moon could be a testing ground for technologies needed for Mars, such as using local resources like lunar ice for water and fuel, and understanding the health effects of lower gravity over months. Mars remains the horizon goal for crewed exploration. It's a daunting challenge. A round trip would take years, and Mars is a harsh environment with a thin CO2 atmosphere, extreme cold, and dust storms. Yet Mars captivates us because it is the most Earth-like planet and held potential for life. Various countries and private companies are actively developing the hardware for Mars journeys. Perhaps in a decade or two, the first human footprints will press into Martian soil. Those explorers might live in habitats, drive rovers across rust-colored deserts, and gaze up at an alien sky where the sun is smaller and the two moons Phobos and Deimos hurtle across the heavens. They will also gaze back toward Earth, now a mere bright star in Mars's twilight, and surely feel the distance, but also the accomplishment of being pioneers on a new world. Farther in the future, who knows what might be possible? If we manage to solve the challenges of fusion power or other advanced propulsion, maybe sending crewed missions to the outer planets, or even interstellar probes, could move from fiction to reality. The idea of generational starships, where those who arrive are the descendants of those who left, has been explored in literature, as has the notion of hibernation or cryogenic sleep for long voyages. We might encounter practical or ethical limits to human expansion, but our curiosity seems boundless. Even if physical travel to the stars proves too difficult, we'll likely send sophisticated robots, or even tiny laser-propelled microprobes, as envisioned by the Breakthrough Starshot initiative to reach Alpha Centauri in a few decades. And if by chance we were to pick up a clear signal from an alien civilization, that would reshape our priorities and dreams overnight. Knowing for sure we are not alone would be a watershed moment in human history. All this exploration, actual or planned, has a way of illuminating the importance of the place we started, Earth. As T.S. Eliot wrote, "The end of all our exploring will be to arrive where we started and know the place for the first time." Every astronaut who has seen Earth from space, even just from orbit, speaks of the overview effect, a powerful emotional realization of the unity and fragility of life on our planet. They see no borders from space, just weather patterns, oceans, and land masses, and a razor-thin atmosphere. Many come back more devoted to protecting our environment and promoting peace. Perhaps when humans live on the Moon or Mars, those distant perspectives will further teach us how special Earth is. A lush, living world in a solar system of barren ones. By exploring dead worlds, we appreciate a living one all the more. Science fiction often speculates on how becoming a multi-planet species might change us. Will we evolve distinct cultures, or even physiques, for different environments, as portrayed in some stories? Will the vast distances dilute our sense of connection? Or will communications technology keep the human family feeling close-knit? These are questions that future generations may answer by lived experience. But our drive to venture outward will likely persist, as it has since humans first left their birthplaces to explore new lands on Earth. Space is the next, endless frontier, not one to conquer in the old sense, but to learn from and coexist with. As we move forward, we carry with us the creative spirit that first painted constellations in the sky and imagined gods among the stars. Our modern myths are the tales of starships and alien encounters. They serve a purpose. They allow us to envision scenarios ahead of reality, to consider how we might react, or how we might build our future societies beyond Earth. They keep our sense of wonder alive, so that the night sky remains not just a scientific object of study, but a canvas for inspiration and reflection. As our journey through the ages draws to a close, we find ourselves gazing up, much as our distant ancestors did, at the same ancient sky. We have traded their myths for telescopes and theories, yet the sense of wonder is undiminished. In fact, it has grown. Each breakthrough, from Copernicus's insight to Galileo's telescope, Newton's laws to Einstein's spacetime, and on to today's cosmic mysteries, has revealed a universe far grander and more mysterious than we could have imagined. We have learned that the Sun is but one star among hundreds of billions in our galaxy, which is itself one of trillions in the observable universe. We have discovered that the elements of our bodies were forged in stars that lived and died long ago. In a literal sense, we are made of star stuff. The iron in our blood, the calcium in our bones. These atoms were cooked in stellar furnaces and scattered across space to become part of us. Thus, the story of the cosmos is our story too. It's humbling and inspiring to realize that we, who once huddled around fires telling tales about the lights in the sky, have now sent spacecraft beyond those lights, walked on the moon, and looked back at our own world from the realm of the planets. Our knowledge has grown by leaps, yet with each answer comes new questions, ensuring that wonder remains. The cosmos has not been conquered. It has been explored and embraced as our broader home, and much of it remains unknown. We still stand at the shore of a vast ocean, the stars like distant shorelights, hinting at lands unseen. We will continue to explore, not because we seek an end to curiosity, but because curiosity is an integral part of who we are. There is a profound comfort in this endless pursuit. On a clear night, when you look up and find the band of the Milky Way arching overhead, consider that you are seeing the combined glow of billions of stars, and that among them are perhaps countless planets, Some may be with dreamers of their own. Across time and space, we are connected to the cosmos. We feel that connection in the tug of gravity that holds us to Earth and binds the planets to the sun. We see it in the starlight that travels years to meet our eyes. We carry it within us in the atoms of ancient suns. The universe is vast beyond comprehension, and yet, as living, thinking beings, we bring meaning to it by marveling at its beauty and unraveling its mysteries. Our exploration of the universe has been a voyage not just outward, but inward as well, revealing the nature of our own existence. We learned that Earth is not the center, but a precious speck in a vast arena. That humbling lesson has, in turn, taught us empathy for our fellow humans and for our fragile planet. The famous pale blue dot image showed us that all we hold dear is on a tiny world suspended in emptiness, emphasizing the folly of our hatreds and the preciousness of our unity. If one day we find others out there or step foot on far-off worlds, it will only deepen our appreciation for the rarity and wonder of life. In the quiet of a starry night, there is a sense of timelessness. Generations before us have looked at these same stars, weaving stories, seeking guidance, feeling small or comforted under their light. Generations after us will do the same. The knowledge we've gained will be their inheritance, and doubtless they will add to it, discovering wonders we can barely imagine. Perhaps they will solve the enigma of dark matter, decode the essence of dark energy, or meet whatever neighbors we have in the galaxy. Or perhaps the true significance lies not just in the discoveries, but in the striving itself, the way that searching the stars gives us purpose and context. And so, we conclude this chapter of our exploration with a gentle optimism. The night sky remains, as it always was, a source of reflection and hope. We can be content in knowing that even as we close our eyes to sleep, above us, the cosmos unfolds in all its splendor. Stars are being born in glowing nebulae. Planets are orbiting in the warmth of suns. Galaxies are colliding in slow dances, and somewhere perhaps other eyes are looking up and wondering as well. The story of the ancient skies, of myths and mysteries, is a story with no end. Each answer is a new beginning, each mystery a call to adventure. Under the eternal night sky, we, the children of stardust, find both humility and greatness. Humility in realizing how small our Earth is in the vast expanse. Greatness in recognizing that our minds can encompass that expanse in thought and imagination. The universe has given us the gift of itself to explore, and in return, we give the universe meaning, simply by being here to witness it. So let us continue to look up in awe and curiosity. Let the stars guide our dreams as they guided the journeys of those before us. In this way, even as we drift into slumber, we remain connected to the cosmos that cradled us into existence. The ancient skies are still above, unchanged for millions of nights, yet forever new to each who gazes in wonder. They invite us to ponder, to learn, and to dream. And as we end our voyage through time and space tonight, we do so with hearts full of calm and minds full of questions, grateful for the beauty and mystery that surround us. The cosmos is vast and strange and magnificent, and we are an inseparable part of it. In that knowledge, we find peace. Good night, and sweet dreams under the ancient skies.